Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists just beyond the edge of what we know to be real, yet close enough to touch with our imagination. Close your eyes for a moment if you'd like, or let them rest softly on these words as they appear before you. Take a deep breath with me, and as you exhale, let the weight of the day begin to drift away like clouds dispersing in a gentle evening breeze. We're about to embark on a journey together, you and I, into a cosmos that might never have existed, yet one that holds profound mysteries about the nature of everything we see when we look up at the night sky. Before we venture too far into this cosmic contemplation, I'd love to know where you're joining me from tonight. Are you nestled in your bed, in a bustling city where the stars struggle to shine through the ambient glow? Perhaps you're in a quiet countryside home, where the Milky Way stretches across your window like a river of light. Or maybe you're somewhere in between, in a suburban room where a few brave stars manage to peek through. Whatever corner of our beautiful Earth you're resting in right now, whatever time zone cradles your evening or morning or afternoon, you're part of this gentle exploration. And if this journey into the cosmos brings you any measure of peace or wonder tonight, perhaps you might consider subscribing to join me on future voyages through these quiet mysteries, or leaving a gentle thumbs up to let me know we've shared something meaningful together in these hours. But there's no urgency to any of that. We have all the time in the universe, quite literally, to explore what we're about to discover. Tonight's question begins with something that might sound impossible at first, something that challenges everything we think we know about how the universe works. What if planets orbited nothing at all? And what if every star in the sky stood perfectly, eternally still? It's a question that seems to defy the very foundations of astronomy, physics, and perhaps even common sense. And yet, it's precisely these kinds of questions, the ones that make us pause and reconsider everything we take for granted, that often lead us to the most profound insights about our cosmos and our place within it. You see, we live in a universe of constant motion, though you'd never know it from the peaceful way the stars appear to us each night. Right now, as you lie there listening to these words, our Earth is spinning on its axis at about 1,000 miles per hour at the equator, though you feel nothing but stillness. We're also orbiting our Sun at roughly 67,000 miles per hour, tracing an invisible ellipse through space that takes us on a journey of nearly 600 million miles each year. Our Sun, meanwhile, isn't standing still either. It's carrying us and all our sister planets on an even grander voyage around the center of our Milky Way galaxy at speeds approaching 500,000 miles per hour. And our entire galaxy, it too is moving, drifting through the cosmic dark toward our neighboring Andromeda galaxy and participating in the vast expansion of space itself. All of this motion, all of this cosmic choreography, happens so smoothly, so quietly, that from our perspective here on Earth's surface, the night sky appears almost frozen in place. The stars seem to hold their positions night after night, year after year, as if painted on a vast dome above us. The planets, those wanderers that gave ancient astronomers their first clues that not everything in the heavens was fixed, trace their predictable paths so slowly that you need to watch for weeks or months to truly appreciate their journeys. It's only when we speed up time, when we compress years into seconds or centuries into minutes, that the true dynamic nature of our cosmos reveals itself. But what if none of that were true? What if we lived in a universe where motion itself had taken a different form, or perhaps had never begun at all? What if every star you see tonight, Sirius blazing in the winter sky, Vega crowning summer evenings, Polaris holding steady in the north, what if they all stood absolutely still, not just apparently still as they seem to us, but truly, fundamentally motionless in space? And what if the planets, including our own Earth, somehow continued their orbital dances but around nothing? No star at the center, no gravitational anchor, just empty space where we expect to find the brilliant heart of a solar system. This might sound like pure fantasy, and in many ways, it is. We're venturing into a realm of imagination tonight, but it's an imagination informed by real science, real physics and real questions that astronomers and cosmologists grapple with every day. Because hidden within this seemingly impossible scenario are seeds of genuine mysteries that surround us even in our real universe. Questions about the nature of space and time, about the invisible forces that govern cosmic motion, about dark matter and dark energy, and about whether the universe we observe is the only possible universe that could exist. As we explore this still sky cosmos together over the next few hours, we'll discover that the line between the impossible and the mysterious is often thinner than we imagine. We'll find that some of the greatest minds in science have actually contemplated scenarios not entirely unlike what we're imagining tonight, and we'll see how asking what-if questions, even seemingly absurd ones, can illuminate profound truths about the nature of reality itself. The ancient Greeks, those first systematic observers of the heavens, believed that the stars were fixed to crystalline spheres that rotated around the Earth. In their cosmos, the stars truly were motionless relative to each other, eternal and unchanging, divine, fixtures in the architecture of heaven. It took thousands of years of careful observation, mathematical innovation, and conceptual breakthroughs to realize that the stars weren't fixed at all, that they were suns like our own, each following their own paths through the vastness of space. Yet there's something deeply appealing about that ancient vision, isn't there? Something comforting about a universe where the patterns in the sky are eternal, where the constellations your ancestors saw are exactly the ones you see, and exactly the ones your descendants would see forever into the future. In our imagined universe tonight, we're going to blend that ancient sense of cosmic stability with modern understanding of planetary motion, creating a hybrid cosmos that never was but perhaps could have been, if the fundamental laws of physics had been written just slightly differently. It's a universe where planets still trace their orbital paths, because without that motion, there would be no days, no years, no cycles of time as we understand them, but where those orbits aren't anchored to burning stars. Instead, they circle points of what? Empty space, invisible masses, knots in the fabric of space-time itself. We'll explore all these possibilities and more, and the stars in our imagined cosmos, those countless suns that in reality are all moving, all following their own trajectories through space. In our thought experiment tonight, they stand perfectly still. Not relative to each other, as they appear to us, but absolutely still in the truest sense. They neither approach nor recede, neither orbit nor drift. They simply exist, burning steadily at their fixed coordinates in space, like eternal lighthouses in an infinite dark ocean. To understand how strange this would be, we need to first appreciate how much motion defines our real universe. Every atom in your body is vibrating with thermal energy. The electrons in those atoms are zipping around their nuclei at significant fractions of the speed of light. The molecules that make up your cells are constantly jostling and bumping into each other. Your blood flows, your lungs expand and contract, electrical signals race through your neurons. At every scale, from the subatomic to the cellular, to the planetary to the galactic, motion is fundamental to the nature of existence as we know it. In thermodynamics, we learn that absolute zero, the complete absence of thermal motion, is actually impossible to achieve. There's always some residual energy, some quantum jittering that prevents perfect stillness. In relativity, we discover that motion and rest are relative concepts. You can never say something is absolutely motionless without specifying what it's motionless relative to. In quantum mechanics, we find that particles can never have perfectly defined positions and zero momentum simultaneously. Uncertainty is built into the fabric of reality at the smallest scales. Yet here we are, imagining a universe where, at least at the cosmic scale, perfect stillness is not only possible but actual. Where stars have definite positions that never change, where the vast machinery of the cosmos is somehow ground to a halt, or perhaps never started spinning in the first place. It's a universe that would require different physics, different fundamental forces, perhaps even different mathematics to describe. And yet, as we'll discover, it's not entirely disconnected from our own universe. There are hints and echoes of such stillness even in our dynamic cosmos, places and phenomena where motion seems to pause, where time appears to slow, where the constant dance of particles and planets and stars takes a breath. Consider for a moment the centre of our galaxy. There, hidden behind vast clouds of dust and gas, lurks a supermassive black hole that astronomers call Sagittarius A star. It's a monster of gravity, containing the mass of more than 4 million suns compressed into a region smaller than the orbit of Mercury. Stars near this black hole whip around it at tremendous speeds, but the black hole itself, this anchor point of our entire galaxy, barely moves at all relative to the average motion of all the stars around it. It's as close to a fixed point as anything gets in our universe, a kind of gravitational throne around which hundreds of billions of stars pay court. Now imagine if every star was like that central black hole, not in terms of gravity or mass, but in terms of stillness. Imagine if every star had found its place in space and simply stayed there. No drift, no orbit around galactic centers, no participation in the expansion of the universe, just perfect, eternal position holding, like notes frozen in a cosmic symphony that never plays. The implications would be staggering. For one thing, the night sky would truly be constant. The constellation Orion, which currently looks like a hunter with a distinctive belt of 3 stars, would maintain that shape not just for the few thousand years of human civilization, but forever. The Big Dipper wouldn't slowly transform over tens of thousands of years as its component stars follow their individual paths through space. The Southern Cross would never drift from southern skies. Every pattern, every asterism, every connect-the-dots figure that humans have ever imagined in the stars would be preserved for eternity. But here's where our thought experiment gets really interesting. Even in this still star universe, we're imagining that planets continue to orbit. But orbit what? In our real universe, planets orbit stars because of gravity. The massive sun at the center of a solar system creates a dent in space-time, and planets roll around the slopes of that dent like marbles circling a drain, never falling in because of their sideways motion, never flying away because of the gravitational pull. It's a delicate balance that has kept Earth circling the sun for over 4 billion years. In our imagined universe, though, if planets orbit nothing, no star, no visible mass, then something else must be keeping them in their paths. Perhaps it's dark matter, that mysterious substance that astronomers tell us makes up about 85% of all the matter in the universe but which we can't see or directly detect. In our real universe, dark matter seems to form vast halos around galaxies, providing extra gravitational pull that keeps stars from flying apart as galaxies rotate. Maybe in our still sky universe, dark matter is condensed into invisible nodes that planets can orbit, phantom anchors that exert gravity without light. Or perhaps the explanation is even stranger. Maybe in this universe, space itself has a different structure. Einstein taught us that massive objects curve space-time, and that this curvature is what we experience as gravity. What if, in our imagined cosmos, space-time could be curved without visible mass? What if there were permanent dents, inherent warps in the fabric of reality that planets could orbit around? These would be like cosmic whirlpools in perfectly still water, unchanging vortices that trap planets in eternal spirals. There's actually some precedent for this kind of thinking in real physics. Scientists have speculated about objects called naked singularities, points of infinite density that aren't hidden behind black hole event horizons. They've theorized about topological defects in space-time, cosmic strings, domain walls, textures that could have formed in the early universe and might still exist today. These are all examples of how space itself might have structure independent of the matter and energy we can see. As you lie there tonight, perhaps you can feel the Earth beneath you continuing its ancient orbit, but imagine that orbit isn't around our familiar sun. Imagine instead that we're circling an absence, a nothing that is somehow something, a center that holds without being. It's a dizzying thought, isn't it? We're so accustomed to thinking of orbits as relationships between objects, Earth and Sun, Moon and Earth, electrons and nuclei, that an orbit around nothing seems like a contradiction in terms. Yet even in our real universe, we encounter situations that aren't so different. When 2 stars orbit each other in what astronomers call a binary system, they don't actually orbit around either star. Instead, they both orbit around their common center of mass, a point in empty space between them. If the stars are equal in mass, this point is exactly halfway between them. If one star is more massive, the center of mass is closer to it, but still not at its center. Both stars trace their paths around this invisible point, this nothing that defines their dance. Take this concept further. In some binary systems, one of the stars is actually a black hole, an object so dense that not even light can escape its gravity. When we observe such systems, we see a visible star orbiting around what appears to be nothing at all. The black hole is there, exerting its gravitational influence, but it's invisible to our telescopes. We only know it exists because of how the visible star moves, tracing an orbit around an apparent void. Now, imagine if every planetary system in our still sky universe was like that. Planets circling invisible partners, dancing with dark companions we cannot see. But unlike black holes, which we can detect through their gravitational effects on nearby matter and light, these invisible centers would be perfectly transparent to everything except the planets bound to them. Light would pass through them unchanged, matter would drift past unaffected, only the planets would feel their pull and respond with orbital devotion. This raises fascinating questions about the nature of planetary systems in such a universe. In our real cosmos, we can tell a lot about a star by studying its planets. The orbits of planets reveal the mass of their star, their spacing tells us about the history of the solar system, their compositions give us clues about the stellar nursery where they all formed. But if planets orbited invisible centers, what would that tell us about the nature of those centers? Would each be unique, or would there be patterns, regularities that would hint at underlying laws? Perhaps in this universe, the invisible centers that planets orbit aren't completely featureless. Maybe they have properties we could measure if we knew how to look. Temperature, perhaps, not heat as we understand it, but some other form of energy that planets can sense and respond to. Or maybe they have something analogous to color, not visible light, but variations in how they interact with different kinds of matter or energy. Each invisible center could be as unique as the stars in our universe, just expressed in ways our current physics doesn't account for. The more we explore this idea, the more we realize how much we take for granted about our own universe. We assume that massive objects must be visible, or at least detectable. We assume that orbits require a massive central body. We assume that the universe operates according to the laws of physics as we understand them. But what if there were other possible universes, other ways for reality to organize itself, other solutions to the cosmic equations that govern existence? This isn't just idle speculation. Modern cosmology seriously considers the possibility of multiple universes, each with potentially different physical laws. String theory suggests there might be 10 to the 500th power possible universes. That's a one followed by 500 zeros, each with its own unique combination of physical constants and force strengths. In some of these universes, stars might not form at all. In others, gravity might be stronger or weaker, changing how objects move and interact. And perhaps, in at least one of these countless possible universes, planets orbit nothing, and stars stand still. As we continue our journey through this imagined cosmos tonight, we'll explore what such a universe might mean for the development of life, for the passage of time, for the nature of space itself. We'll consider how astronomers in such a universe might study the heavens, what kinds of theories they might develop, what mysteries they might uncover, and throughout it all we'll keep one foot in our own universe, using the contrast to better appreciate the cosmic dance we're all part of, even when it feels like we're standing still. The beauty of thought experiments like this one is that they don't require us to choose between imagination and reality. We can hold both in our minds simultaneously, letting each illuminate the other. The impossible universe we're exploring tonight makes the actual universe we inhabit seem both more precious and more mysterious. Every time you look up at the night sky after tonight, you might find yourself newly aware of all the motion hidden in that apparent stillness, all the invisible forces shaping what we see, all the questions we haven't even thought to ask yet. And perhaps that's the real value of asking, what if the cosmos were completely different? It reminds us that the cosmos as it actually is remains largely unknown to us. We've mapped only a tiny fraction of the stars in our galaxy. We can't see or directly detect most of the matter in the universe. We don't fully understand why the expansion of the universe is accelerating. We don't know if our universe is unique or one of countless others. We don't know if the laws of physics we've discovered are inevitable or arbitrary. In many ways, the real universe is just as mysterious as any imagined alternative. So as you settle deeper into your rest tonight, as your breathing naturally slows and your mind begins to drift, let yourself float in this space between the real and the imagined. Feel the Earth beneath you, supposedly orbiting our sun at tremendous speed, yet feeling perfectly still. Look up at the stars, whether through your window or in your mind's eye, and see them both as they are, distant suns racing through space, and as they appear, eternal lights fixed in the heavens. Hold both visions gently without needing to choose between them. We live, you and I, in a universe that never stops moving, though you'd hardly know it from the profound stillness that surrounds us in these quiet moments. As you rest there, perhaps with your eyes closed or gazing softly at the ceiling, it might seem that everything is perfectly still. Your room isn't moving, your bed isn't shifting, the building around you stands motionless. And yet, as we've begun to explore, this stillness is one of the most beautiful illusions in all of nature. Every atom, every molecule, every planet and star participates in an endless cosmic ballet that has been unfolding for nearly 14 billion years. Let's begin with something close to home. The ground. Beneath you. It feels solid, stable, unchanging. But that earth, that foundation you're resting on, is actually the surface of a massive sphere of rock and metal that's spinning through space like a cosmic top. The Earth rotates once every 24 hours, which means that if you're near the equator, you're actually moving eastward at over 1,000 miles per hour right now. If you're closer to the poles, you're moving more slowly, but you're still spinning. This rotation is so smooth, so constant that we don't feel it at all. There's no wind in your face from this motion, no sense of acceleration or deceleration. It's like being on the smoothest train ride imaginable, one that never speeds up, never slows down, never takes a curve sharp enough for you to notice. This rotation gives us our days and nights, of course. The sun isn't actually rising and setting, we're spinning toward it and away from it, like a cosmic rotisserie slowly turning before a stellar flame. Every sunrise you've ever witnessed, every sunset that has painted the sky in oranges and purples, has been the result of this steady spin, and it's been happening for billions of years, since the Earth first formed from a disk of dust and gas surrounding our infant sun. The energy of that formation, the angular momentum of that primordial cloud is still with us, still turning our world in its daily pirouette. But the Earth's rotation is just the beginning of our motion through space. As we spin, we're also orbiting the sun in a grand ellipse that takes us on a journey of roughly 584 million miles each year. This orbital motion is much faster than our rotation. We're travelling around the sun at approximately 67,000 miles per hour. That's about 30 kilometers every second. In the time it takes you to take a deep breath, you've moved hundreds of miles through space. By the time you finish listening to this chapter, you'll be thousands of miles from where you started, though of course you'll never notice the difference. This orbit too is so smooth that we don't feel it directly. There's a common misconception that we should feel the Earth's motion through space, like we feel motion in a car or airplane, but motion through the vacuum of space is fundamentally different from motion through air. There's no resistance, no friction, no reference points whizzing by to give us a sense of speed. We're falling around the sun in a perfect balance, moving fast enough that we don't spiral inward, but not so fast that we fly off into the darkness. It's a cosmic equilibrium that has kept our planet in the habitable zone, that sweet spot where water can exist as a liquid, for billions of years. The shape of Earth's orbit is nearly circular, but not quite. It's an ellipse, which means sometimes we're a little closer to the sun. That happens in early January, and sometimes we're a little farther away. That's in early July. The difference is only about 3 million miles, which might sound like a lot, but it's only about 3% of our average distance from the sun. This variation doesn't cause our seasons, by the way. Those come from the tilt of Earth's axis, but it does mean that our orbital speed varies slightly throughout the year. We move a bit faster when we're closer to the sun, a bit slower when we're farther away, following laws of planetary motion that Johannes Kepler figured out 400 years ago by carefully studying the motion of Mars. And speaking of other planets, they're all dancing their own orbital dances around the sun. Mercury, the innermost planet, races around the sun in just 88 Earth days, moving at over 100,000 miles per hour. Venus, shrouded in clouds, takes about 225 days for its orbit. Mars, the red planet that so captivated Kepler, needs nearly 2 Earth years to complete one circuit. And then there are the giants. Jupiter with its 12-year orbit, Saturn taking nearly 30 years, Uranus requiring 84 years, and distant Neptune needing 165 years to make a single journey around our star. All of these planets, including Earth, orbit in roughly the same plane, like marbles rolling on an invisible disk. This isn't a coincidence, it's a consequence of how our solar system formed. About 4.5 billion years ago, a vast cloud of gas and dust began to collapse under its own gravity. As it collapsed, it began to spin, and as it spun, it flattened into a disk, much like pizza dough flattens when a chef spins it. The sun formed at the center of this disk, and the planets formed from the material orbiting around it. That's why we all orbit in the same direction and in approximately the same plane. We're all children of the same cosmic pizza. But our solar system's motion doesn't stop with planets orbiting the sun. Our entire solar system, sun, planets, asteroids, comets, and all, is moving through space as part of our galaxy's rotation. The sun and its entourage are located about 26,000 light-years from the center of the Milky Way, in what astronomers sometimes call the Orion Arm or local spur. From this position, we're orbiting around the galactic center at the impressive speed of about 514,000 miles per hour. Even at this tremendous velocity, it takes us about 230 million years to complete one orbit around the galaxy. The last time our solar system was in this part of its galactic orbit, dinosaurs were just beginning to appear on Earth. This galactic rotation isn't like the solid rotation of a wheel or a record on a turntable. Instead, it's what astronomers call differential rotation. Stars closer to the galactic center orbit faster than those farther out, but not in the simple way that planets closer to the sun orbit faster. The galaxy's rotation is influenced by the distribution of both visible matter, stars, gas and dust, and invisible dark matter, which seems to form a vast halo around our galaxy. In fact, it was the study of galactic rotation that first convinced astronomers that dark matter must exist. The stars at the edges of galaxies were moving too fast to be held by the gravity of visible matter alone. Something invisible was providing extra gravitational pull, keeping the galaxies from flying apart. As we orbit the galactic center, we're not traveling in a simple circle or ellipse. Our path takes us slightly above and below the galactic plane in a gentle wave motion, like a horse on a carousel that goes up and down as well as around. This oscillation takes about 60 million years to complete, meaning we bob up and down through the galactic disk about 4 times during each galactic orbit. Some scientists have suggested that this motion might affect life on Earth. Perhaps when we pass through the denser parts of the galactic disk, we're more likely to encounter cosmic hazards like supernovae or clouds of interstellar material. But this remains a topic of active research and debate. Our galaxy itself isn't standing still either. The Milky Way is moving through space at about 1.3 million miles per hour relative to the cosmic microwave background radiation, which is the closest thing we have to a universal reference frame. We're heading in the general direction of a massive collection of galaxies called the Great Attractor, though we'll never actually reach it because the expansion of the universe is carrying it away from us, even faster than we're moving toward it. And yes, the universe itself is expanding. This is perhaps the strangest motion of all, because it's not motion through space, but motion of space. The fabric of space-time itself is stretching, carrying galaxies apart from each other like raisins in a rising loaf of bread. This expansion was discovered by Edwin Hubble in the 1920s, when he noticed that almost all galaxies appeared to be moving away from us, and the farther away they were, the faster they seemed to be receding. This isn't because we're at the center of some cosmic explosion. Every galaxy sees every other galaxy moving away from it. It's because space itself is expanding everywhere, all at once. The expansion of the universe adds yet another layer to our cosmic motion. Not only are we spinning, orbiting the sun, circling the galaxy, and moving through intergalactic space, but the space we're moving through is itself expanding. It's like running on a treadmill that's on a train that's on a boat that's in a current. Motions within motions within motions, each with its own speed and direction. What's even more remarkable is that this expansion appears to be accelerating. In the late 1990s, astronomers studying distant supernovas discovered that the expansion of the universe isn't slowing down due to gravity as everyone expected, it's speeding up. This acceleration is attributed to something we call dark energy, a mysterious force or property of space itself that seems to push everything apart. Dark energy makes up about 68% of the total energy density of the universe, but we have almost no idea what it actually is. It's one of the biggest mysteries in modern cosmology, a reminder that even our moving universe holds secrets we've barely begun to uncover. Now, let's bring our attention to something more intimate: the motion of the stars themselves. When you look up at the night sky, The stars seem fixed in their constellations, eternal and unchanging. But this too is an illusion born of the vast distances involved. Every star you can see is moving through space at its own speed and in its own direction. Astronomers call this proper motion, and while it's too slow for us to notice over a human lifetime, it's quite real and measurable with precise instruments. Take Barnard's star, for example, a small red dwarf about 6 light-years from Earth. It has the highest proper motion of any star visible from Earth, appearing to move about 10 arcseconds per year across the sky. That might not sound like much. It would take about 180 years for it to move the width of the full moon. But over thousands of years, this motion adds up. The constellations our ancestors saw were slightly different from the ones we see, and the constellations our descendants will see will be different still. Even our North Star, Polaris, which seems so steadfast and reliable, won't always be our North Star. Due to the wobble of Earth's axis, a slow gyration called precession that takes about 26,000 years to complete, different stars take turns being the pole star. 12,000 years ago, the bright star Vega was the pole star. 5,000 years ago, when the ancient Egyptians were building the pyramids, the pole star was Thuban in the constellation Draco. And 12,000 years from now, Vega will be the pole star again. The sky itself is a slowly turning kaleidoscope, its patterns shifting over millennia. Some stars are moving so fast that they're actually escaping from our galaxy. These hypervelocity stars have been flung out by close encounters with the supermassive black hole at our galaxy's center, or by the explosion of a companion star in a binary system. They're racing through intergalactic space at speeds of up to 2 million miles per hour, fast enough to escape the Milky Way's gravitational pull entirely. Imagine being on a planet orbiting one of these stars. You'd be on an intergalactic voyage, watching the Milky Way slowly shrink behind you as you headed out into the cosmic void. Other stars are in complex orbital dances with companions. More than half of all stars are part of binary or multiple star systems, where 2 or more stars orbit around their common center of mass. Some of these systems are so close that the stars actually touch, sharing their outer atmospheres in a cosmic embrace. Others are so far apart that they take millions of years to complete one orbit around each other, and some systems are even more complex, hierarchical systems where pairs of stars orbit around other pairs, creating intricate gravitational choreographies that would make Newton's head spin. The planets in our own solar system showcase their own complex motions beyond their simple orbits around the Sun. They rotate on their axes at different rates. Jupiter spins once in just under 10 hours, while Venus takes 243 Earth days to rotate once. They wobble and precess, their axes slowly shifting over thousands of years. Their orbits themselves slowly change due to gravitational interactions with other planets, a cosmic perturbation that creates subtle variations in their paths through space. Even our Moon, that familiar companion in the night sky, has a more complex motion than you might expect. It doesn't just orbit Earth in a simple circle. Its orbit is elliptical, bringing it closer and farther from us over the course of each month. The Moon also librates, appearing to rock back and forth slightly, which allows us to see about 59% of its surface over time rather than just 50%. And the Moon is slowly spiraling away from Earth, moving about 1.5 inches farther from us each year due to tidal interactions. Billions of years ago, the Moon was much closer, and days were much shorter. Billions of years from now, if the Sun doesn't engulf us first, the Moon will be so far away that total solar eclipses will no longer be possible. All of this motion, from the vibration of atoms to the expansion of the universe, is interconnected in ways that we're only beginning to understand. The rotation of the Earth affects the circulation of our atmosphere and oceans. The orbit of Earth around the Sun drives our seasons and climate patterns. The motion of our solar system through the galaxy may influence the rate of cosmic ray bombardment we experience. The expansion of the universe determines the ultimate fate of all cosmic structures. And yet, for all this motion, there are places in our universe where things move very, very slowly. In the vast voids between galaxy clusters, where matter is spread incredibly thin, particles might drift for millions of years without encountering anything else. Near absolute zero, in laboratories here on Earth, scientists have created Bose-Einstein condensates, where atoms move so slowly they almost seem to stop. And at the event horizons of black holes, from an outside observer's perspective, time dilation makes falling objects appear to slow down and freeze, their final moments stretched out to infinity. These extremes of motion, from the fantastic speeds of hypervelocity stars to the near stillness of ultra-cold atoms, show us the incredible range of what's possible in our universe. Motion isn't just something that happens in our universe. In many ways, motion is what makes our universe what it is. Without motion, there would be no energy. Without energy, there would be no heat. Without heat, there would be no stars. Without stars, there would be no heavy elements. Without heavy elements, there would be no planets. Without planets, there would be no life. We are, in a very real sense, children of motion, products of 13.8 billion years of cosmic dynamics. As you lie there in the darkness, feeling the illusion of stillness while actually participating in this cosmic dance, perhaps you can sense the delicate balance that keeps it all working. Every motion in the universe, from the smallest to the largest scale, follows precise mathematical laws. The same equations that describe a pendulum swinging in a grandfather clock also describe planets orbiting stars. The same principles that govern the fall of an apple also govern the structure of galaxies. There's a profound unity underlying all this motion, a set of fundamental rules that seem to apply everywhere and at every scale. But what if those rules were different? What if the universe had been set up with different initial conditions, different constants, different forces? This brings us back to our central thought experiment, a universe where planets orbit nothing and stars stand still. Such a universe would need fundamentally different physics, a completely different set of cosmic rules. And yet, as we'll explore in our next chapter, even such an impossible-seeming universe might have its own strange logic, its own peculiar beauty, its own way of making sense. For now, though, let's appreciate the universe we actually inhabit, this cosmic dance hall where everything is always in motion. Feel the Earth spinning beneath you, carrying you through your day-night cycle. Feel it orbiting the Sun, carrying you through your yearly journey. Feel the Sun carrying our entire solar system around the galaxy, a 250 million-year orbit that our species has experienced only a tiny fraction of. Feel the galaxy moving through intergalactic space, part of a cosmic web of matter in motion, and feel space itself expanding, carrying everything apart in a grand cosmic diaspora that began with the Big Bang and continues to this moment. All of this motion happens so smoothly, so quietly, that we can lie in perfect comfort and contemplate it all. We can close our eyes and feel perfectly still, while actually moving at combined speeds that dwarf anything we can achieve with our fastest rockets. We can look up at stars that seem eternal and fixed, while knowing they're all on their own journeys through space and time. We can exist in this moving universe precisely because the motion is so regular, so predictable, so mathematically elegant that it creates islands of stability where complexity can emerge and flourish. Now we arrive at the heart of our cosmic mystery, the central impossibility that we've gathered here tonight to explore together. Imagine, if you will, a planet like Earth, blue with oceans, swirled with white clouds, green and brown with continents, following its familiar orbital path through space. It traces the same ellipse it has always traced, taking the same 365.25 days to complete its journey. But when we look to the center of that orbit, expecting to find a brilliant star, a gravitational anchor, the massive body that explains this eternal circling, we find nothing. Not darkness hiding something, not a black hole swallowing light, but genuine absolute nothing. Empty space where our sun should be, void where we expect substance, absence where we require presence. How could such a thing be possible? In our universe, as we understand it, orbits are relationships. They're the visible expression of invisible forces, the dance that results when gravity and motion find their balance. Every orbit we've ever observed, from electrons around atomic nuclei to moons around planets, to planets around stars to stars around galactic centers, has been an orbit around something. Even when that something is invisible, like a black hole or a concentration of dark matter, it's still there, still real, still exerting its gravitational influence. But what we're imagining tonight challenges this fundamental assumption. We're imagining planets that somehow maintain their orbital motion without any central mass to orbit around. Let's sit with this impossibility for a moment and really try to understand what it would mean. In our normal universe, gravity is what creates orbits. a massive object like the Sun curves the fabric of space-time around it, creating what we might think of as a valley or a depression. Planets roll around the slopes of this valley, their forward motion keeping them from falling in, the curved space keeping them from flying away. It's a beautiful balance, one that has fascinated physicists and astronomers since Newton first realized that the force pulling an apple to Earth was the same force keeping the Moon in its orbit. But if there's no mass at the center, no sun or star or any other gravitating body, then what creates the valley? What curves the space-time that the planets follow? This is where our imagination must stretch beyond conventional physics and consider possibilities that might exist in a universe with different rules, different structures, different fundamental principles than our own. One possibility is that in this imagined universe, space-time itself has inherent curvature independent of mass. Perhaps when this universe formed, in its own version of a Big Bang or through some other cosmic genesis we can barely imagine, certain regions of space were born with permanent warps, eternal valleys that would forever after guide the motion of any matter that happened to form near them. These wouldn't be warps caused by mass, they would be features of space itself, as fundamental and unchangeable as the three dimensions of space and one of time that define our cosmic stage. Think of it like this. Imagine a rubber sheet that represents space-time. In our universe, we place a heavy ball on the sheet to create a depression, and marbles rolled near that depression will circle around it. But what if, instead of placing a ball on the sheet itself was manufactured with a depression already in it? What if the very fabric of space-time came pre-warped, with built-in valleys that don't need mass to maintain them? Planets forming near these inherent warps would naturally fall into orbital patterns, circling around nothing because the nothing is actually a permanent feature of space itself. This might sound completely fantastic, but there are actually hints in our own universe that something like this could be possible. Einstein's field equations, which describe how matter and energy curve space-time, also have solutions that don't require any matter at all. These are called vacuum solutions, and they describe space-times that are curved even in the complete absence of mass and energy. The simplest of these is flat, empty space, but there are others that are more exotic. Some describe rotating spacetimes, others describe expanding or contracting spaces, and still others describe complex topologies that twist back on themselves in mind-bending ways. Another possibility for our planet's orbiting nothing scenario involves invisible matter, not the familiar dark matter that astronomers have inferred from galactic rotation curves and gravitational lensing, but something even more exotic. Perhaps in this universe there exists a form of matter that interacts with normal matter only through gravity, and even then, only with certain kinds of normal matter. It would be selective in its gravitational pull, attracting planets but not affecting light, gas, dust, or any of the other things we normally use to detect massive objects. This selective gravity might seem impossible, but consider that in our universe, we already have forces that affect some particles but not others. The electromagnetic force affects charged particles but not neutral ones. The strong nuclear force affects quarks but not electrons. The weak nuclear force affects all fermions but has different strengths for different particles. So perhaps in our imagined universe, gravity itself could be selective, could choose what to attract and what to ignore. If such selective invisible matter existed at the centers of planetary orbits, it would create one of the strangest astronomical situations imaginable. Astronomers in such a universe would observe planets clearly following orbital paths, but no amount of searching would reveal what they're orbiting. Light would pass through these invisible centers unaffected. Interstellar gas and dust would drift past without accumulating. Comets might pass right through the space where a star should be without any deflection of their path. Only planets, for whatever cosmic reason, would feel the gravitational pull and respond with orbital motion. But let's push our imagination even further. What if the explanation isn't invisible matter or pre-curved spacetime, but something about the nature of motion itself in this universe? In our cosmos, we have a principle called inertia. Objects in motion tend to stay in motion unless acted upon by a force. This is why planets, once they're orbiting, continue to orbit. They have momentum that carries them forward, and gravity bends that forward motion into a closed path. But what if in our imagined universe, certain kinds of motion were simply fundamental properties of space? Imagine regions of space where circular or elliptical motion is the natural state. The way straight-line motion is natural in our universe's empty space. A planet entering such a region wouldn't need a central mass to orbit around. It would simply begin following the curved paths that are inherent to that region of space. It would be like a train that doesn't need tracks because certain parts of the landscape naturally guide wheels in specific directions. The orbits would be there whether planets followed them or not, invisible grooves in the fabric of reality itself. This concept might seem to violate our intuitions about cause and effect, about the need for forces to create accelerated motion. But remember, we're imagining a universe with different fundamental laws. In our universe, we take it for granted that space is isotropic, the same in all directions, and homogeneous, the same everywhere. But what if space in this other universe had a grain to it, a preferred structure that made certain motions more natural than others? Wood has a grain that makes it easier to split in one direction than another. Crystals have preferred axes along which they cleave. Perhaps space itself could have such properties, making orbital motion the path of least resistance in certain regions. Consider too the possibility that what we're calling nothing at the center of these orbits might be something we simply can't perceive or understand with our current physics. In our universe, we've discovered that what we once thought was empty space is actually teeming with quantum fluctuations, particle-antiparticle pairs popping into existence and annihilating each other in timeframes too brief to measure directly. We've learned that the vacuum has energy, that empty space has properties, that nothing is actually quite something. Perhaps in our imagined universe, the centers of planetary orbits are occupied by something even more exotic than quantum foam, structures or entities that exist partially outside the normal dimensions of space and time. They might be anchored in higher dimensions that we can't perceive, extending into our three-dimensional space only through their gravitational effects, and even then, only in ways that affect planets. It would be like seeing the shadow of a four-dimensional object. We observe its effects but can never see the thing itself because it exists partially outside our perceptual realm. These higher dimensional anchors might explain not just why planets orbit nothing visible, but also why different planetary systems might have different characteristics despite having no visible central star. Perhaps the shape and strength of the higher dimensional structure determines the number of planets that can orbit it, their distances, their orbital periods. Each invisible center might be unique, a different kind of knot or fold in higher dimensional space, creating a unique gravitational signature that only planets can read. Let's also consider what the absence of a central star would mean for these planets. In our solar system, the sun doesn't just provide gravitational anchorage, it's also the source of light and heat that makes life possible on Earth. It drives our weather, powers photosynthesis, and creates the day-night cycle that regulates so much of life's activity. Without a central star, planets in our imagined universe would be dark and cold, unless they had some other source of energy. Perhaps these planets generate their own heat through radioactive decay in their cores, like a scaled-up version of the heat that still warms Earth's interior billions of years after its formation. Or maybe they're heated by tidal forces from their mysterious orbital motion itself, the constant flexing of the planet as it follows its path around nothing generating friction and warmth. Or possibly, in this strange universe, the very act of orbiting nothing generates energy through some exotic physics we can't fathom, a kind of gravitational dynamo that converts orbital motion directly into heat and light. The planets might even glow with their own light, not reflected starlight but genuine planetary luminescence. Imagine Earth-like worlds that shine with a soft blue-green light, gas giants that glow like dim orange lanterns, ice worlds that emit a pale white radiance. Each planet would be its own light source, creating a very different kind of night sky for any observers on their surfaces. Instead of distant star points, you might see the soft glows of neighbouring planets in their own orbits around nothing, like fireflies circling an invisible flame. What would it be like to live on such a world? Without a sun to rise and set, there would be no natural day-night cycle, unless the planet's own rotation somehow generated one through varying its self-generated light. Seasons might still exist if the planet's axis was tilted, but they would be seasons of changing planetary light rather than changing solar input. The sky might be forever dark except for the planet's own aurora-like glows and the distant lights of other planets in the system. Navigation would be entirely different. We've used the sun and stars to find our way for thousands of years, but on a planet orbiting nothing, with stars that never move, as we'll explore more fully later, you'd need different methods. Perhaps the planet's own magnetic field would be stronger and more stable, providing a reliable compass. Or maybe the invisible center of the orbit, despite being undetectable to light, would create other effects, subtle gravitational variations, patterns in cosmic rays, distortions in space-time that could be used for orientation. The development of astronomy on such a world would follow a completely different path than it did on Earth. Early astronomers wouldn't have the motion of the sun to track, wouldn't see the wandering of planets against fixed stars, since the stars themselves would be still, as we'll discuss. They might not even realize they were orbiting anything at all until they developed sophisticated enough instruments to detect their own orbital motion through other means, perhaps by observing the Doppler shift of distant galaxies as their planet moved toward and away from them in its orbit, or by detecting the subtle parallax of nearby stars despite those stars being motionless. The discovery that they were orbiting nothing, that there was no central mass anchoring their motion, would be a profound philosophical and scientific crisis. It would challenge every assumption about cause and effect, about the relationship between matter and motion, about the fundamental nature of reality. Scientists would have to develop entirely new theories of gravity, new models of space-time, new mathematics to describe motion without a gravitational source. They might discover that their situation wasn't unique, that throughout their universe, planets orbit invisible centers while stars stand still. This would lead to fascinating questions about the formation of such systems. In our universe, planets form from the same collapsing cloud of gas and dust that forms their central star. But how would planets form around nothing? Perhaps in this universe, the invisible centers, whatever they are, act as seeds for planetary formation, attracting and organizing matter in their vicinity without being made of matter themselves. Or perhaps planets form first, and their collective presence somehow creates or attracts the invisible centers they orbit. It might be that once enough matter gathers in a region and begins to rotate, it generates a kind of gravitational echo, a standing wave in space-time that persists even after the matter has organized itself into discrete planets. The planets would then orbit this echo of their own creation, trapped in a gravitational pattern they themselves generated. There's something poetic about this idea. Worlds circling the memory of their own formation, orbiting the ghost of their birth cloud, forever following paths carved out by their own collective past. It would mean that planetary systems are self-organizing, self-sustaining structures that don't need stars to exist. They would be like cosmic whirlpools that maintain themselves, through their own motion, stable patterns in the fabric of space-time that could persist for billions of years. As we contemplate these planets orbiting nothing, we might also wonder about the stability of such systems. In our universe, planetary orbits can be disrupted by passing stars, by gravitational interactions with other planets, by the gradual evolution of their central star. But if there's no central star, and if other stars don't move, as in our imagined universe, would these planetary systems be more stable or less so? Perhaps without a massive central body, the planets would be more susceptible to perturbations, more likely to drift from their orbits or collide with each other. Or maybe the opposite would be true. Without the gravitational dominance of a central star, the planets might find more democratic, mutually stable configurations, their orbits locked in resonances that could last forever. Each planet would orbit not just the invisible center, but also, in a sense, all the other planets, creating a complex but stable gravitational symphony. The invisible centers themselves might evolve over time, even if we can't see them. Perhaps they slowly evaporate, their gravitational influence weakening over cosmic timescales until eventually the planets drift free. Or maybe they grow stronger, feeding on some exotic energy we don't understand, gradually pulling their planets into tighter and tighter orbits. There might even be life cycles to these invisible centers: birth, maturity, death, played out entirely in gravitational terms, invisible to light but profound in their effects on the worlds that orbit them. As we near the end of this contemplation of planets without centers, let's consider one more possibility, perhaps the most mind-bending of all. What if the reason planets orbit nothing in this universe is that the planets themselves are the fundamental reality, and everything else, including space and time, is secondary? What if orbital motion isn't something planets do but something planets are? In this view, planets wouldn't be objects moving through space. They would be persistent patterns in the fabric of reality itself, standing waves in the cosmic medium, knots in the quantum field. Their orbits wouldn't be paths through space but rather the shape of their existence, the way they manifest in four-dimensional space-time. They wouldn't orbit nothing because there would be no distinction between the planet and its orbit. They would be one and the same thing, a unified phenomenon that we only perceive as separate because of our limited perspective. This would mean that asking, what do planets orbit, is like asking, what do waves wave through? Or, what do knots tie around? The question assumes a separation that doesn't actually exist. The planets and their orbits around nothing would be singular phenomena, irreducible features of this strange universe, as fundamental as particles and forces are in ours. As you lie there in the darkness, perhaps you can feel the profound mystery of motion itself. In our universe, we orbit a star we can see and feel, but imagine drifting through space, following an ancient path around an invisible center, held by forces we don't understand, part of a cosmic dance whose music we cannot hear. It's a haunting image, isn't it? Worlds in the dark, circling nothing, maintaining their stately paths through space, for reasons that might forever remain mysterious. And yet, there's also something beautiful about it. These planets would be independent in a way ours could never be, not dependent on a star for their orbital stability. They would be self-contained worlds, each carrying its own light if any, each following its own path around its own invisible center. They would be like cosmic hermits, alone but not lonely, isolated but still part of the grand structure of their universe. The transition between our contemplation of orbiting planets and still stars is like crossing a bridge between two impossible ideas, each one strange enough on its own, but together creating a universe so foreign to our experience that it challenges our very notion of what a universe can be. As we prepare to explore the nature of stars that never move, remember that these still stars would be watching over planets that orbit nothing, creating a cosmic tableau of motion without cause and stillness without reason. A universe that exists in the space between what we know and what we can imagine. Above you tonight, whether you can see them through your window or only in your mind's eye, the stars appear to hold their eternal positions, forming the patterns that humanity has gazed upon for thousands of years. Orion the Hunter, the Big Dipper, the Southern Cross, these celestial landmarks seem as permanent as mountains, as unchanging as the laws of physics themselves. But this permanence, as we've discovered through centuries of careful observation, is merely an illusion born of distance and the brevity of human life. The stars are all in motion, all following their own paths through the galaxy, slowly rearranging the heavens in a cosmic ballet that unfolds over millions of years. But what if this wasn't true? What if the stars really were fixed, truly motionless, frozen in place for all eternity? In our imagined universe, this is exactly what we find. Every star, from the dimmest red dwarf to the most brilliant blue supergiant, stands absolutely still in space. They don't orbit the galactic center. They don't drift through the spiral arms. They don't approach or recede from one another. They simply exist at fixed coordinates in the cosmic void, burning steadily at their appointed positions like eternal lighthouses in an infinite dark sea. The implications of such stillness are profound and strange, touching everything from the basic physics of how stars work to the philosophical meaning of permanence and change. To truly appreciate what still stars would mean we need to first understand just how much stellar motion shapes our actual universe. In our cosmos, stars are born in vast clouds of gas and dust called nebulae, where gravity pulls material together until nuclear fusion ignites. But these stellar nurseries are themselves in motion, orbiting the galaxy, colliding with other clouds, being compressed by shock waves from supernovae. The stars that form inherit this motion, emerging from their birth clouds with velocities and directions that send them on individual journeys through space. Some stars travel together in groups, clusters that formed from the same nebula, and continue to move through space as cosmic families. The Pleiades, those beautiful seven sisters visible to the naked eye, are such a cluster, about 400 light-years from Earth, and moving together through space at about 40 kilometers per second. Over the next few million years, they'll gradually disperse as gravitational interactions with other stars and the galaxy itself pull them apart. but for now they travel as companions through the cosmic dark. Other stars are cosmic wanderers, ejected from their birthplaces by gravitational encounters or supernova explosions, now travelling alone through interstellar space. Barnard's star, which we mentioned earlier, is racing through our stellar neighbourhood at about 140 km per second relative to the Sun. In about 10,000 years it will pass within 4 light-years of our solar system, briefly becoming one of our nearest stellar neighbours before continuing on its lonely journey. But in our imagined universe of still stars, none of this motion exists. Stars would burn where they formed, or perhaps where they were placed at the universe's beginning, never moving, never changing position relative to one another. The constellations wouldn't just appear permanent, they would be permanent. The star patterns that hypothetical beings see at the universe's beginning would be the same patterns they see at its end, assuming stars continue to shine that long. This raises immediate questions about how such stars could even exist. In our universe, stellar motion is intimately connected with stellar formation and evolution. Stars form from collapsing, rotating clouds of gas, and conservation of angular momentum means they're born spinning and moving. They're influenced by the gravity of nearby stars, pulled by the galactic centre, pushed by radiation pressure from neighbouring stellar winds. To have truly motionless stars, you'd need a universe with fundamentally different physics, where somehow stars could form and exist without any of the forces that create motion in our cosmos. Perhaps in this still star universe, stars didn't form through gravitational collapse at all. Maybe they were created in place during this universe's version of the Big Bang, appearing fully formed at their fixed positions like light switching on across the cosmic dark. Each star would be a fundamental feature of space-time itself, as intrinsic to the universe's structure as the dimensions of space and time. They wouldn't be objects in space so much as features of space, permanent modifications to the cosmic fabric that happen to emit light and heat. Or perhaps stars in this universe did form through some process, but one that doesn't impart motion. Imagine if gravity worked differently, if it could pull matter together to form stars without creating any net momentum. The gas and dust would simply condense in place, like dew forming on a spider's web, gradually accumulating until fusion ignited. Once formed, these stars would have no reason to move because they'd have no initial velocity, and with no other stars moving either, there would be no gravitational interactions to set them in motion later. The physics of such motionless stars would be fascinating to contemplate. In our universe, many stars are kept stable by rotation. Their spin helps balance the inward pull of gravity. Without any motion at all, including rotation, stars in our imagined universe would need different mechanisms to maintain their stability. Perhaps they'd be perfectly spherical, with pressure balances so precise that no rotation is needed. Or maybe the laws of physics in this universe simply don't require rotation for stability, allowing stars to burn peacefully without any motion whatsoever. Consider what this would mean for stellar evolution. In our universe, stars change over their lifetimes. They exhaust their hydrogen fuel, expand into red giants, shed their outer layers, collapse into white dwarfs or neutron stars or black holes. Much of this evolution is influenced by interactions with companion stars, by the acquisition of new material from their surroundings, by the loss of mass through stellar winds that are shaped by motion through the interstellar medium. But still, stars would evolve in isolation, each one aging according to its own internal processes without any external influences. Would such stars live longer or shorter lives than the moving stars in our universe? Without motion through the interstellar medium, they wouldn't encounter fresh clouds of gas to accrete. Without orbital dynamics, binary star systems couldn't exist, eliminating all the exotic evolutionary paths that come from stellar interactions. No type Y supernovae from white dwarfs stealing mass from companions, no X-ray binaries, no stellar mergers. Each star would be born alone, live alone, and die alone, its fate determined entirely by its initial mass and composition. The death of still stars would be particularly strange. When massive stars in our universe explode as supernovae, they often impart tremendous velocities to any remaining stellar core, creating neutron stars that can race through space at hundreds of kilometers per second. But in a universe where stars don't move, what would happen to these remnants? Would neutron stars and black holes also remain perfectly still, frozen at the exact position where their progenitor star once burned? It would be like having cosmic tombstones, markers in space showing where stars once lived and died. The distribution of stars in such a universe would tell a very different story than what we see in our cosmos. In our universe, stars are distributed in galaxies, vast collections held together by gravity and dark matter, with spiral arms and elliptical shapes that reflect billions of years of gravitational evolution. But if stars don't move, could galaxies even exist in any meaningful sense? There would be no spiral arms because those require orbital motion. There would be no galactic collisions or mergers. There might not even be any large-scale structure at all, just stars distributed throughout space according to whatever process created them, frozen in that primordial arrangement forever. Perhaps stars would be distributed uniformly throughout space, like a three-dimensional grid of lights extending infinitely in all directions. Or maybe they'd be arranged in patterns that reflected the initial conditions of this universe's birth, frozen ripples from whatever event created space-time and filled it with stars. These patterns would be like reading the universe's birth certificate, a permanent record of the cosmic beginning written in the positions of still stars. For any beings living on planets in such a universe, remembering that these planets orbit invisible centers, as we explored earlier, the night sky would have a very different character. Without proper motion, there would be no parallax from stellar movement, making it much harder to determine the distances to stars. The traditional methods of stellar astronomy would need to be completely reimagined. How would you measure the distance to a star that never moves, that shows no parallax even over centuries of observation from a planet that itself is orbiting? Nothing. Perhaps astronomers in such a universe would develop different techniques entirely. They might focus on the intrinsic properties of starlight, spectroscopy, photometry, polarimetry, to understand stellar nature without relying on motion-based measurements. They might discover that even though stars don't move through space, their light still carries information about distance through some other mechanism. Perhaps a subtle redshift or blue shift that depends on how space itself is structured rather than on relative motion. The concept of time itself might be different in a universe of still stars. In our cosmos, we use stellar motion as one of our fundamental clocks. The Earth's rotation relative to the stars gives us our sidereal day. The precession of the equinoxes caused by the gravitational influence of the Sun and Moon on Earth's equatorial bulge gives us a 26,000-year cycle that ancient astronomers used to mark the Great Ages. But if stars don't move, these cosmic clocks wouldn't exist. Time would have to be measured purely through local phenomena, planetary rotations and orbits, radioactive decay, the aging of stars themselves. Still stars would also profoundly affect how we think about causality and connection in the universe. In our cosmos, everything influences everything else, even if very slightly. The gravity of distant stars affects our solar system. Stellar winds from neighboring stars can trigger or inhibit star formation. Supernova can send shockwaves across light years, but perfectly still stars would be causally isolated from each other in many ways. They could still exchange light, still influence each other gravitationally if gravity exists in this universe as we know it, but there would be no dynamic interactions, no stellar encounters, no exchange of material between stars. This isolation might extend to communication as well. In our universe, we dream of interstellar travel, of journeys between the stars, of civilizations spreading across the galaxy. But in a universe where stars don't move and planets orbit invisible centers, such travel might be fundamentally different. Without moving stars to provide gravitational slingshots, without stellar winds to catch in solar sails, space travel would require different technologies and strategies. The vast distances between stars would be even more daunting when those stars are truly fixed, offering no opportunities for clever orbital mechanics to aid the journey. Yet there's something hauntingly beautiful about the idea of still stars. Imagine looking up at a night sky knowing that every star you see has been in exactly that position since the universe began, and will be in exactly that position until the universe ends. The constellation you trace with your finger is not just apparently eternal, but truly eternal. The star your ancestors wished upon is exactly, precisely, absolutely the same star you see tonight. Not just the same star, but in the exact same position, unchanged by the passage of eons. This permanence would create a different relationship between conscious beings and the cosmos. In our universe, we're acutely aware that everything changes, that the stars themselves are temporary, that even the patterns we see in the sky are fleeting on cosmic timescales. This knowledge can be both humbling and unsettling. But beings in a still-star universe would live under an eternal sky, a cosmic constant that would provide a fundamentally different context for existence. Would they be more comfortable with permanence, less anxious about change? Or would the unchanging heavens make them more acutely aware of their own mortality, their own brief flicker of existence against an eternal backdrop? The mythology and philosophy that might develop under still stars is fascinating to consider. Our human myths are full of stories about stars and constellations, heroes placed in the heavens, gods walking across the sky, cosmic dramas played out in stellar movements. But what stories would beings tell about stars that never move? Perhaps they'd see them as eternal watchers, cosmic eyes that have observed everything that has ever happened and will happen. Or maybe they'd view them as a kind of cosmic prison, lights trapped forever in place, unable to explore or change or grow. Religion and spirituality might take different forms as well. Many of our spiritual traditions incorporate the idea of cosmic cycles, of heavenly movements reflecting divine will, of astronomical events marking significant moments. But in a universe of still stars, divinity might be associated with permanence rather than change, with stability rather than dynamism. The divine might be seen as the force that holds the stars in place, that maintains the eternal order against the chaos of planetary motions around invisible centers. Let's also consider what kinds of stars could exist in such a universe. In our cosmos, stellar variety is partly a result of different formation conditions. Stars born in metal-rich regions versus metal-poor regions. Stars formed in dense clusters versus isolated formations. Stars influenced by nearby supernovae or stellar winds. But if all stars in this universe formed simultaneously and in isolation, they might be much more uniform. Perhaps they'd all have similar masses, similar compositions, similar colors and temperatures. The night sky might be filled with billions of nearly identical stars, like a vast field of uniform candles. Or perhaps the opposite would be true. Without the homogenizing effects of stellar motion and mixing, each star might be utterly unique, its properties determined by purely local conditions at its point of formation. You might have red giants next to white dwarfs, blue supergiants beside brown dwarfs, all frozen in an eternal tableau of stellar diversity. The sky would be like a cosmic museum, displaying every possible type of star in permanent exhibition. The boundaries between star systems would be absolute in such a universe. In our cosmos, stars occasionally pass close to each other, exchanging comets, disrupting planetary orbits, sometimes even trading planets. The Oort cloud at the edge of our solar system is occasionally stirred by passing stars, sending comets falling toward the inner solar system. But with still stars, each system would be forever isolated. The boundaries between stellar influences would be fixed and permanent, creating distinct zones of gravitational influence that never overlap or change. This might lead to very different distributions of matter in space. In our universe, interstellar space contains gas and dust that moves between star systems, enriched by supernovae, swept up by stellar winds, constantly recycled through generations of stars. But in a still star universe, each bit of interstellar matter would eventually fall under the influence of the nearest star and stay there. Over billions of years, all the loose matter in the universe might be swept up, leaving perfectly empty voids between stellar systems. What about stellar remnants in such a universe? When stars die in our cosmos, they leave behind white dwarfs, neutron stars, or black holes that continue to move through space, sometimes finding new companions, sometimes merging with other remnants, sometimes just cooling slowly in isolation. But still star remnants would be even more isolated, frozen at their death positions forever. The universe would gradually fill with these dark monuments to expired stars, invisible markers of where light once shone. Black holes would be particularly interesting in a still star universe. In our cosmos, black holes can grow by consuming nearby matter, merge with other black holes, and even evaporate slowly through Hawking radiation. But stationary black holes would have limited opportunities to grow. Only matter that happened to be within their initial sphere of influence could fall in. They'd be like cosmic drains that could never be moved, forever fixed at specific points in space, slowly evaporating over unimaginable timescales, if Hawking radiation exists in this universe as it does in ours. The large-scale structure of such a universe would be fundamentally different from what we observe. Our universe has a cosmic web of galaxy clusters and filaments, separated by vast voids, a structure that emerged from tiny quantum fluctuations in the early universe, amplified by billions of years of gravitational evolution. But without moving stars, no such structure could develop. The universe would retain whatever distribution it started with, a frozen snapshot of its initial conditions preserved forever. This brings us to a profound question. Could life and intelligence evolve in a universe of still stars? We've already imagined that planets somehow orbit invisible centers, which might provide the changes and cycles necessary for evolution. But the broader cosmic environment would be very different. There would be no stellar migrations bringing new elements to different regions of space, no supernovae triggering star formation in neighboring regions, no galactic collisions creating bursts of stellar birth. Each region of space would be isolated, evolving only according to its own internal processes. Perhaps life in such a universe would be more diverse, with each planetary system developing in complete isolation, never influenced by cosmic events from outside. Or perhaps it would be less diverse, with fewer opportunities for the kind of cosmic disruptions that might trigger evolutionary innovations. The development of intelligence might follow completely different paths, shaped by the eternal constancy of the heavens rather than the dynamic cosmos we know. As we contemplate these still stars frozen in their positions for all eternity, we might wonder about the ultimate fate of such a universe. In our cosmos, we envision various possible endings: the Big Rip, the Big Freeze, the Big Crunch, all involving motion of some kind. But a universe of still stars might have a different fate entirely. Perhaps it would simply fade slowly as stars exhaust their fuel and die, leaving an ever-darkening sky filled with cold remnants. Or perhaps the strange physics that keeps stars still would also provide some mechanism for renewal, some way for new stars to form in place of the old, maintaining an eternal cosmic equilibrium. The boundary between possible and impossible becomes beautifully blurred when we consider still stars. On one hand, everything we know about physics and cosmology tells us that such stars cannot exist. Motion is fundamental to how stars form, live, and die. On the other hand, the universe constantly surprises us with phenomena that once seemed impossible. Black holes, dark energy, quantum entanglement. Who's to say that somewhere in the vast multiverse there isn't a cosmos where stars stand perfectly still, eternal sentinels in the dark? Time, as you experience it lying there in the darkness, seems to flow steadily forward, marked by your heartbeat, your breathing, the soft ticking of a clock perhaps, or the gradual lightening of the sky if dawn approaches where you are. We measure our days by the Earth's rotation, our years by its orbit around the sun, our cosmic ages by the slow dance of stars across the heavens. But what becomes of time itself in a universe where stars stand still and planets orbit nothing? How would beings in such a cosmos measure the passage of moments, the accumulation of years, the deep flow of cosmic history? This question touches the very heart of what time means, both physically and philosophically. In our universe, time and motion are inextricably linked. Einstein showed us that time and space are not separate entities, but aspects of a unified space-time, where motion through space affects the passage of time. The faster you move through space, the slower you move through time, though this effect only becomes noticeable at velocities approaching the speed of light. But more fundamentally, we use motion to measure time: the swing of a pendulum, the vibration of a quartz crystal, the decay of radioactive atoms, the orbit of celestial bodies. In our imagined universe of still stars and planets orbiting invisible centers, the celestial clockwork would be profoundly different. There would be no stellar parallax marking Earth's journey around the sun, no gradual precession of the equinoxes, no slow drift of stars across the sky marking the passage of centuries. The heavens would be like a stopped clock, its hands frozen at some eternal moment, offering no guidance about the flow of time on scales longer than a planetary orbit. Yet time would still exist in such a universe, wouldn't it? Planets would still rotate, creating days and nights for any beings on their surfaces. They would still orbit their invisible centers, marking out years in their eternal circling. Atoms would still vibrate, radioactive elements would still decay, light would still take time to travel from place to place. the microscopic clocks of quantum mechanics and thermodynamics would still tick, even if the macroscopic clock of stellar motion had stopped. This creates a fascinating dichotomy, a universe where time exists at some scales but not others, where local time flows but cosmic time stands still. It would be as if the universe had multiple temporal dimensions, some flowing and some frozen, creating a complex temporal topology that beings within it would have to navigate and understand. Let's imagine living on a planet in such a universe. Your days would still come and go with your planet's rotation. You would still age, still experience the sequential flow of moments that consciousness seems to require. But when you looked up at the night sky, you would see eternity itself, stars that have never moved and never will move, a cosmic moment frozen forever above you. It would be like living in a universe-sized room where all the clocks on the walls have stopped, but your wristwatch keeps ticking. The psychological impact of such a sky would be profound. We humans have always used the heavens as our ultimate timekeeper. Ancient astronomers tracked the movements of planets to predict seasons and eclipses. Navigators used the positions of stars to determine not just where they were, but when they were, calculating longitude by comparing local time to the time at a reference meridian. Even today, our most precise time standards reference astronomical phenomena: the rotation of the Earth, the orbit of the Earth, the vibrations of cesium atoms that ultimately calibrate to cosmic rhythms. But beings under a still sky would have to develop entirely different relationships with time. Without moving stars to mark the centuries, they might focus more intensely on shorter cycles, the phases of their moons if they have them, the orbits of neighbouring planets around their own invisible centres, the life cycles of organisms, the rise and fall of civilizations. Their sense of deep time might be more abstract, less tied to celestial mechanics, and more to geological or biological processes. Consider how they might write their history. We mark our eras by astronomical events, the precession of equinoxes giving us astrological ages, the cycles of solar activity affecting climate and culture, the appearance of comets and supernovae marking significant moments in our chronicles. But in a universe of still stars, history would be marked differently, perhaps by the slow cooling of their planet's core, the gradual evolution of life, the accumulation of impact craters from asteroids that somehow still move even though stars don't. The development of physics in such a universe would follow a different path. Our understanding of time has been shaped by observations of celestial motion. Newton's conception of absolute time was influenced by the regular movements of planets. Einstein's revelation that time is relative came partly from thinking about the synchronization of clocks using light signals between moving trains. But physicists in a still star universe might develop different theories of time, perhaps ones where time is more fundamentally separate from space, where temporal and spatial dimensions follow different rules. They might discover that time in their universe has a different structure than what we're familiar with. Perhaps time flows at different rates in different regions of space, not because of gravitational fields or relative motion, but as an inherent property of space-time itself. Some regions might be temporally thick, where time passes slowly, while others are temporally thin, where it races by. Planets orbiting through these regions would experience varying rates of time, their clocks speeding up and slowing down as they trace their paths around nothing. Or perhaps they discover that time in their universe is quantized in a way ours isn't, not flowing smoothly but jumping from moment to moment in discrete steps, like a cosmic movie playing at a very high but finite frame rate. The still stars might be still precisely because they exist between frames, frozen in the gaps between temporal quanta, while planets somehow jump from frame to frame, creating the illusion of smooth motion. The thermodynamics of time would be particularly interesting in such a universe. In our cosmos, the arrow of time, the fact that time seems to flow in only one direction is intimately connected with the increase of entropy, the tendency of systems to become more disordered over time. This is why we can scramble an egg but not unscramble it, why ice cubes melt in warm water but never spontaneously form, why the universe as a whole is moving from a state of low entropy to high entropy. But in a universe where stars don't move, entropy would behave differently. The still stars would represent vast reservoirs of low entropy that never mix, never spread their energy to their surroundings through motion. Each star would be like an isolated system, burning through its fuel in perfect isolation, unable to share its entropy with the wider universe. The universe as a whole might have multiple arrows of time, local arrows pointing from low to high entropy within each stellar system, but no global arrow connecting them all. This could lead to regions of space where time effectively runs backward, at least from a thermodynamic perspective. If entropy decreased in some region, perhaps through some exotic process we can't imagine, time then might flow in reverse. You could have neighbouring regions of space where time flows in opposite directions, separated by boundaries where time stands still. Crossing such boundaries would be like stepping through a temporal mirror, entering a realm where effects precede causes, where memory becomes prophecy. The biology of time in such a universe would also be unique. Life on Earth evolved in response to celestial cycles, circadian rhythms tied to the day-night cycle, seasonal behaviours linked to the year, even longer cycles possibly connected to astronomical variations. But life under still stars would evolve different temporal patterns. Without a moving sky to provide seasonal variations, organisms might develop their own internal calendars, perhaps based on magnetic field fluctuations, radioactive decay, or other planetary phenomena. Intelligent beings in such a universe might perceive time very differently than we do. Without the cosmic clock of stellar motion, they might be more aware of subjective time, the way time seems to slow during moments of intense experience or speed up during routine activities. They might develop philosophies where consciousness itself is the fundamental measure of time, where the universe's temporal flow is determined not by physical processes but by the presence of observers to experience it. Their mathematics of time might be richer and stranger than ours. Where we use simple linear time coordinates in most of our equations, they might need complex temporal manifolds to describe their reality. Time might have multiple dimensions in their physics, not just past or future, but other temporal directions we can't even conceive. Moving through time might be as complex as moving through space, requiring navigation through temporal landscapes with their own geography and obstacles. Music and art in such a universe would have different relationships with time. Our music is deeply connected to cosmic rhythms, the beat of our hearts, which evolved in response to Earth's gravity and atmosphere, the cycles of tension and resolution that mirror the cycles of day and night, season and year. But beings under still stars might create music based on different temporal patterns, the slow pulse of radioactive decay, the quick flicker of quantum fluctuations, the complex polyrhythms of planets orbiting invisible centers at different rates. Their visual arts might be more focused on capturing permanence rather than change. Where our paintings and photographs often try to freeze moments from a flowing world, their art might celebrate the eternal stillness of their stars, finding beauty in the unchanging rather than the transient. Or perhaps, surrounded by cosmic permanence, they'd be even more fascinated by change, creating art that emphasizes the few things in their universe that do move and evolve. The concept of progress might be different in such a universe. We often think of progress as movement, forward through time, upward in complexity, outward in space. But in a universe where the larger structures don't move, progress might be conceived differently, perhaps as deepening rather than advancing, as increasing internal complexity rather than external expansion, as exploring the infinite possibilities within fixed boundaries rather than pushing those boundaries outward. Memory and history would take on special significance in a universe of still stars. With no cosmic changes to mark the passage of eras, the only record of time's passage would be in the memories of living beings, the geological records of planets, the gradual burning out of stars. History wouldn't be written in the sky but in more subtle places. The accumulation of impact craters, the evolution of life, the rise and fall of civilizations on planets orbiting nothing. They might develop technologies we can't imagine for measuring and manipulating time. Without stellar motion to provide a cosmic clock, they might discover ways to measure time directly, to see its flow the way we see the flow of water or wind. They might learn to store time, to slow it down or speed it up locally, to create temporal lenses that let them see into the past or future. Their relationship with time might be more active, less passive acceptance of its flow and more direct engagement with its nature. The philosophy of time in such a universe would grapple with profound questions. If the stars are eternal and unchanging, does that mean the universe itself is eternal? Did it have a beginning? Will it have an end? Or does it exist in an eternal present with only local pockets of change? Are there still stars outside of time somehow, existing in a different temporal dimension than the planets that orbit nothing? Is time fundamental to reality, or is it an emergent property that only exists where there is motion and change? Death and mortality would be viewed through a different lens. In our universe, we take comfort in the fact that everything changes, that even stars are born and die, that nothing is permanent except change itself. But beings in a still-star universe would live with the knowledge that some things truly are eternal, that the stars watching over them have always been there and always will be. Would this make death seem more final, more absolute? Or would it make life seem more precious, a brief dance of change in a cosmos of stillness? They might discover connections between consciousness and time that we haven't imagined. Perhaps consciousness in their universe is what creates time, what allows change to occur in a cosmos that would otherwise be frozen. Maybe the planets orbit and atoms vibrate only because conscious beings observe them, and without consciousness even these motions would cease. Time might not be a stage on which consciousness acts, but a phenomenon that consciousness creates. The search for life elsewhere in such a universe would be different too. We look for signs of life by searching for atmospheric changes, radio signals, the waste heat of civilizations, all things that involve change over time, but in a universe where time works differently, the signatures of life might be different. Perhaps life there leaves temporal footprints rather than physical ones, alterations in the flow of time that mark where consciousness has been present. As their science advanced, beings in this universe might discover that their still stars and orbiting planets are just one aspect of a larger temporal structure. Perhaps there are other dimensions of time they can't perceive directly, where the stars are actually moving rapidly, where cosmic evolution proceeds at scales they can't access. Their universe might be like a single frame from a cosmic movie, frozen from one perspective but part of a larger story from another. They might even discover ways to transcend the temporal limitations of their universe. If time there is structured differently than in our cosmos, perhaps it's more malleable, more subject to conscious influence. They might learn to step outside the normal flow of time, to experience their universe from a temporal perspective where the stars do move, where cosmic evolution is visible, where the full story of their reality becomes clear. The ultimate questions about time in such a universe might be unanswerable, just as they are in ours. What is time really? Why does it flow in one direction? Is it continuous or discrete? Is there a smallest unit of time? Does time exist independently of consciousness? Or do we create it by observing it? These questions would be even more acute in a universe where time seems to work differently at different scales, where stillness and motion coexist in ways that challenge intuition. Imagine for a moment the great observatories of our imagined universe, these temples to cosmic curiosity where beings point their instruments toward the still stars and planets, orbiting nothing, trying to decode the mysteries of their strange cosmos. Picture telescopes not unlike our own, massive mirrors gathering ancient light, sensitive cameras recording every photon, spectrographs splitting starlight into rainbow fingerprints, but aimed at a fundamentally different sky. What would these instruments reveal? What stories would the data tell? How would astronomers in such a universe piece together the nature of their reality from the light and gravity and radiation that reaches their senses? In our universe, much of what we've learned about the cosmos comes from observing motion. We measure the distances to nearby stars through parallax, watching them appear to shift position as Earth orbits the Sun. We determine the masses of stars by observing how they orbit each other in binary systems. We discovered the expansion of the universe by noticing that galaxies are moving away from us. Their light shifted toward the red end of the spectrum. We map dark matter by observing how its gravity affects the motion of visible matter. Motion is the key that has unlocked most of cosmic secrets. But in a universe where stars stand still and planets orbit invisible centers, astronomers would need entirely different techniques. Their telescopes would see a cosmos frozen in an eternal moment, stars that never shift position, never change their brightness due to orbital mechanics, never reveal their masses through gravitational dances with companions. It would be like trying to understand a symphony by looking at a single, frozen moment of the orchestra, every musician caught mid-note, their instruments silent and still. Let's start with the most basic astronomical measurement, distance. In our cosmos, we use a cosmic distance ladder, each rung building on the previous one. Parallax gives us distances to nearby stars, which lets us calibrate the brightness of certain types of stars, which lets us use those stars as standard candles to measure greater distances and so on. But parallax requires that stars have fixed positions relative to more distant stars, while appearing to move due to Earth's orbital motion. In a universe of truly still stars, even this apparent motion wouldn't exist. Every star would remain in exactly the same position in the sky throughout the planet's orbit around its invisible centre. Astronomers in such a universe might need to rely entirely on intrinsic properties of starlight to determine distance. Perhaps they'd discover that light itself carries information about how far it has travelled, not through redshift caused by cosmic expansion, which might not exist in their universe, but through some other mechanism. Maybe photons accumulate a kind of cosmic timestamp as they travel, a subtle change in their quantum properties that reveals their journey time. Or perhaps the interaction between light and the strange physics that keeps stars still would create distance-dependent effects that could be measured with sensitive enough instruments. The spectrographs in these observatories would reveal fascinating puzzles. In our universe, stellar spectra show Doppler shifts from stellar rotation and orbital motion, broadening of spectral lines from stellar atmospheres in motion, splitting of lines from magnetic fields in rotating stars. But the spectra of still stars would be different. Perhaps impossibly sharp spectral lines with no Doppler broadening, revealing details of stellar atmospheres that we can never see in our universe of moving stars. These spectra might show that the stars, while motionless in space, are still dynamic internally, with convection and stellar winds and magnetic fields all operating within the constraint of perfect positional stillness. Or perhaps the spectra would reveal something even stranger, that the stars aren't quite as still as they appear. Maybe they vibrate in place, oscillating at frequencies too low or too high for direct observation, but detectable through careful spectroscopic analysis. These stellar vibrations might be the only motion allowed in their frozen positions, a kind of cosmic humming that carries information about stellar mass, composition, and age. Astronomers might learn to read these vibrations like musical notes, each star singing its own unique chord in the cosmic silence. The photometry, the measurement of stellar brightness, would tell different stories too. In our universe, many stars vary in brightness due to orbital mechanics, eclipsing binaries, rotation, star spots rotating in and out of view, or pulsation, Cepheid variables. But still stars might show different patterns of variability. Perhaps they pulse in place, their brightness fluctuating as they undergo internal cycles we don't see in moving stars. Or maybe their brightness would be eerily constant, more stable than any star in our universe, creating perfect standard candles for distance measurement if astronomers could find another way to determine their intrinsic luminosity. Radio telescopes in this universe would detect a cosmic background very different from what we observe. Our cosmic microwave background radiation carries the echo of the Big Bang, stretched and cooled by the expansion of the universe, showing tiny fluctuations that seeded the formation of galaxies. But in a universe of still stars, the background radiation might be different, perhaps perfectly uniform if there was no cosmic evolution, or showing strange patterns that reflect the mechanism that keeps stars frozen in place. Radio astronomers might detect signals we can't imagine, the electromagnetic signature of planets orbiting nothing, the radio echo of invisible centers, the whisper of whatever force maintains cosmic stillness. Gravitational wave detectors, if they could be built in such a universe, would be particularly revealing. In our cosmos, gravitational waves are created by accelerating masses, binary black holes spiraling together, neutron stars colliding, supernovae exploding asymmetrically. But in a universe where stars don't move, traditional sources of gravitational waves wouldn't exist. Yet the planets orbiting invisible centers would be accelerating constantly in their circular paths. Would they generate gravitational waves? And if so, what would those waves reveal about the nature of the invisible centers? Perhaps gravitational wave astronomers would discover that the invisible centers aren't completely invisible to gravity waves. Maybe these mysterious anchors of planetary orbits create a unique gravitational signature, a kind of gravitational color that reveals their nature even though they can't be seen with light. The gravitational wave background of such a universe might be rich with information about these invisible structures, creating a kind of gravitational map of cosmic architecture that optical telescopes could never reveal. Neutrino detectors would provide another window into this strange cosmos. In our universe, neutrinos stream from the nuclear fusion in stellar cores, from supernovae, from cosmic ray interactions. But still stars might produce different neutrino signatures. Without stellar motion to Doppler shift the neutrino energies, detectors might be able to make incredibly precise measurements of stellar nuclear processes. They might discover that neutrinos in their universe carry information about the invisible centers that planets orbit, perhaps passing through these mysterious structures in ways that reveal their properties. The cosmic ray detectors would face unique puzzles. In our universe, cosmic rays are accelerated by shock waves from supernovae, by magnetic fields around pulsars, by jets from black holes. But in a universe of still stars, these acceleration mechanisms might not exist. Where would cosmic rays come from? Perhaps from the boundaries between regions of space with different temporal properties, or from the interaction between normal matter and whatever creates the invisible centers. The energy spectrum and composition of cosmic rays might be completely different, telling a story of cosmic processes we haven't imagined. X-ray and gamma-ray telescopes would observe a high-energy universe unlike anything we know. Without binary systems where matter transfers between stars, without stellar collisions, without the shock waves from stellar motion through interstellar medium, many of our familiar X-ray sources wouldn't exist. But perhaps new sources would take their place. The X-ray glow from planets grinding against the fabric of space-time as they orbit nothing. Gamma-ray flashes from the rare events when matter interacts with invisible centers. High-energy radiation from the boundaries between moving and still regions of the cosmos. The infrared telescopes would map the thermal universe, detecting the heat from stars, the warm glow of planets, the faint emission from interstellar dust. But in a universe where things don't move and mix, the thermal patterns might be very different. Each star might be surrounded by a perfectly spherical shell of warm dust that never disperses, never mixes with material from other stars. Planets might have strange thermal signatures as they orbit through regions of space with different properties, heating and cooling in patterns that reveal the invisible structure of their orbits. As technology advanced, these astronomers might develop entirely new types of telescopes, instruments designed specifically for their still universe. Perhaps they'd create temporal telescopes that can see the flow of time itself, revealing which regions of space have different temporal properties. Or gravitational lenses that can focus the gravitational influence of invisible centers, making them observable through their warping of space-time even though they emit no light. They might develop quantum telescopes that can detect the quantum properties of distant stars, reading information encoded in the quantum states of photons that classical instruments miss. The data from all these instruments would paint a picture of a universe profoundly different from ours, yet following its own elegant logic. Astronomers might discover that the still stars are arranged in patterns that encode fundamental information about their universe, mathematical constants, physical laws, even instructions for understanding the invisible centers that planets orbit. The cosmic architecture might be a kind of message, a user's manual for the universe written in the positions of eternal stars. They might find evidence that their universe isn't entirely still after all. Perhaps there are regions where different rules apply, cosmic domains where stars do move, where normal gravity exists, where physics works more like it does in our universe. The boundaries between these regions would be areas of intense scientific interest, cosmic laboratories where different physical laws meet and interact. Telescopes aimed at these boundaries might observe phenomena that bridge the gap between stillness and motion, providing clues about why their universe is the way it is. The search for exoplanets would be particularly challenging. In our universe, we detect planets around other stars through various methods, watching stars wobble from planetary gravity, seeing stars dim as planets pass in front of them, directly imaging planets in infrared light. But if stars don't move, they wouldn't wobble. If planets orbit invisible centers rather than stars, they wouldn't create transits. Direct imaging might be the only option, but it would reveal a bizarre cosmos where planets float in apparently empty space, circling nothing visible, lit by their own internal heat or faint phosphorescence rather than reflected starlight. The discovery of life elsewhere would require new approaches. Our SETI programs search for radio signals, look for atmospheric biosignatures, watch for the waste heat of advanced civilizations. But in a universe of still stars and strange physics, the signatures of life might be different. Perhaps life there leaves temporal footprints, alterations in the flow of time that mark where biology has been active. Or maybe living planets have different gravitational signatures than dead ones, their orbits around invisible centers subtly influenced by the presence of life. Advanced civilizations in such a universe might be detected through their manipulation of the strange physics that governs their cosmos. Perhaps they learn to move stars, breaking the cosmic stillness in ways that would be visible across vast distances. Or they might create artificial invisible centers, engineering new planetary orbits, building cosmic structures that exploit the unique physics of their universe. The telescopes might detect the engineering signatures of civilizations that have learned to work with stillness rather than motion. The data centers of these observatories would be filled with measurements that challenge understanding. Computer models trying to explain how stars can remain perfectly still, how planets can orbit nothing, how time can flow differently in different regions of space. The equations would be unlike anything in our physics textbooks, describing a cosmos that operates on principles we haven't discovered. Machine learning algorithms might find patterns in the data that biological minds can't perceive, revealing deep structures in the apparent randomness of still star positions and invisible center distributions. International or interplanetary collaborations would pool data from telescopes on different worlds, each orbiting its own invisible center, each providing a unique perspective on the frozen heavens. By combining observations from multiple planets, astronomers might be able to triangulate distances to stars without traditional parallax, measure the three-dimensional structure of their galaxy without stellar motion, map the invisible centers through their cumulative gravitational effects. The greatest discoveries might come from the longest observations. Patient astronomers might maintain continuous observations of the same stars for centuries or millennia, looking for changes that occur on timescales longer than individual lives. They might discover that the stars, while still in space, undergo slow evolutionary changes, gradually brightening or dimming, slowly changing color, eventually dying in ways unique to still stars. These long-term observations would be like time-lapse photography of geological processes, revealing the slow cosmic changes that short-lived beings would otherwise miss. Some telescopes might be designed not to observe the universe as it is, but to search for evidence of how it became this way. They might look for fossil light from a time before the stars stopped moving, cosmic archaeology searching for traces of an earlier, more dynamic cosmos. Or they might search for regions where the process of stillness is still happening, boundaries where moving stars are captured and frozen, where the strange physics of their universe is actively converting motion into stillness. The philosophers working alongside the astronomers would grapple with the implications of what the telescopes reveal. If planets orbit invisible centers that can't be detected by any instrument, do those centers really exist, or are they just a convenient fiction to explain planetary motion? If stars have been still forever, did the universe have a beginning, or has it always existed in its current state? If different regions of space have different physical laws, what determines which laws apply where? The public observatories where ordinary citizens can look through telescopes would offer a different experience than in our world. Instead of tracking objects across the sky, following planets in their wanderings, watching for meteors and comets, observers would engage with a static but perhaps more deeply mysterious sky. They might spend hours studying the spectra of individual stars, looking for the subtle variations that reveal stellar moods. They might watch planets in their strange orbits, trying to perceive the invisible centers they circle. They might participate in citizen science projects to map the eternal positions of stars, creating ever more detailed charts of their frozen heavens. Children, looking through their first telescopes, wouldn't experience the thrill of seeing Saturn drift across the field of view or watching Jupiter's moons dance around their parent planet. Instead, they might experience the deeper mystery of seeing planets suspended in empty space, held by invisible forces circling nothing. They might wonder, as all children do, why? But in their universe, the question would have different implications, touching on the fundamental nature of existence in a cosmos that defies our understanding. The telescopes of this universe would be windows not just into space, but into mystery itself. Every observation would raise more questions than it answers. Every measurement would deepen the puzzle of how such a cosmos could exist. The astronomers working with these instruments wouldn't just be mapping the heavens, they would be detectives trying to solve the ultimate cosmic crime. Who or what stole motion from the stars and gave planets invisible partners to dance with? As our imagined astronomers compile their observations, build their theories, and push the boundaries of what their instruments can detect, they might begin to suspect that their universe is not alone. Perhaps their telescopes, pushing to greater distances and sensitivities, would detect hints of other universes, regions where different physics applies, where stars move and planets orbit visible suns. The boundary between their still universe and these dynamic realms would become the focus of intense study, the place where they might finally understand why their cosmos is the way it is. The data streaming from these telescopes would tell a story we can barely imagine, a narrative of a cosmos that operates on principles foreign to our experience. Yet in their dedication to understanding, in their ingenuity in developing new instruments and techniques, in their wonder at the mysteries their telescopes reveal, these astronomers would be exactly like us. Conscious beings trying to comprehend the incomprehensible, using technology to extend their senses beyond biological limits, reaching always for a deeper understanding of the cosmic home they inhabit. The telescopes would see a universe of profound stillness, punctuated by mysterious motion, of visible stars that don't move and invisible centers that anchor planetary orbits, of time that flows differently in different places, of physics that challenges every assumption. They would see a cosmos that shouldn't exist according to our understanding, yet one that follows its own beautiful, if alien, logic. And in trying to understand what their telescopes reveal, the beings in this universe would embark on the same journey we're on. The quest to understand not just how the universe works, but why it exists at all and what our place in it might be. Beneath the visible universe we've been exploring tonight, beneath the still stars and the planets orbiting nothing, beneath the strange flows of time and the mysteries revealed by patient telescopes, there must be some deeper framework holding it all together, some invisible architecture that explains how planets can orbit without central masses, how stars can remain perfectly motionless, how such a cosmos can exist at all. As you rest there in the darkness, let's descend together into these hidden depths, exploring the secret structures that might underlie a universe so different from our own, yet perhaps not as impossible as it first seemed. In our cosmos, we've grown accustomed to the idea that what we see is not all there is. Dark matter, that mysterious substance that makes up most of the universe's mass, reveals itself only through its gravitational effects. Dark energy, even more mysterious, drives the accelerating expansion of space itself. Quantum fields permeate all of space, invisible yet fundamental to the behavior of particles and forces. The vacuum itself seethes with virtual particles and zero-point energy. We live in a universe where the invisible far outweighs the visible, where hidden frameworks determine the behavior of everything we can see. But in our imagined universe of still stars and orbiting planets, the hidden frameworks would need to be even more exotic, even more fundamental to the structure of reality. They would need to explain not just how things move, but how they can orbit nothing, how they can stand still forever, how the basic rules of cause and effect can be so different from what we know. These frameworks wouldn't just modify the behavior of matter and energy, they would define the very nature of space, time, and existence itself. Let's begin with the gravitational framework, or whatever passes for gravity in this strange cosmos. In our universe, gravity is described by Einstein as the curvature of space-time caused by mass and energy. Massive objects create valleys in the fabric of space-time, and other objects roll into these valleys, creating what we perceive as gravitational attraction. But if planets orbit empty space where no mass exists, then either gravity works differently, or something else is creating the necessary curvature. Perhaps in this universe, space-time has what we might call memory. When matter first formed in this cosmos, however that happened, it might have created gravitational impressions that persisted even after the matter moved or disappeared. These gravitational ghosts, these persistent warps in space-time, could be what planets orbit. Imagine dropping a heavy ball on a stretched rubber sheet, then removing the ball but having the depression remain, frozen in place forever. Planets would roll around these permanent depressions, orbiting the memory of mass rather than mass itself. This gravitational memory might explain not just planetary orbits, but also why stars stand still. Perhaps when stars formed, they created such deep impressions in space-time that they became gravitationally locked in place, unable to move without enormous energy input. They would be like balls that have rolled into holes so perfectly fitted to them that they can spin in place but never climb out. The entire visible universe would be trapped in a gravitational landscape established at the moment of creation, with every star and planet confined to its predetermined position or path. But gravitational memory is just one possibility. Another framework might involve what we could call selective gravity, a force that affects different types of matter in different ways. In our universe, gravity is universal. It affects all matter and energy equally, at least at the scales we can measure. But what if gravity in this imagined universe discriminates? What if it pulls on planets but not on light, on solid matter but not on gas, on objects above a certain mass but not below it? This selective gravity might operate through extra dimensions that we can't perceive directly. String theory in our universe suggests there might be many more than the 4 dimensions we experience. Perhaps in this imagined cosmos, planets extend into these extra dimensions in ways that stars don't, making them subject to forces that leave stars unaffected. The invisible centers that planets orbit might be knots or structures in these higher dimensions, visible and influential only to objects that extend into those dimensional spaces. Consider the possibility of what we might call field lines in space, invisible channels or grooves that guide matter in specific ways. Just as magnetic field lines guide charged particles, these spatial field lines might guide planets in their orbits. These wouldn't be electromagnetic or gravitational fields as we know them, but something more fundamental, perhaps related to the basic topology of space itself. Planets would follow these field lines like trains on invisible tracks, unable to deviate from their prescribed paths even though nothing visible constrains them. These field lines might be 3-dimensional, creating complex networks throughout space. Where field lines loop back on themselves, planets orbit. Where they run straight, objects would move in straight lines if they could move at all. Where field lines don't exist, matter couldn't exist either. True voids in the fullest sense. The pattern of field lines would determine the entire structure of the universe, from the distribution of stars to the orbits of planets, to the boundaries between regions of different physics. The quantum framework of such a universe would be particularly fascinating. In our cosmos, quantum mechanics describes the behavior of matter and energy at the smallest scales, with particles existing in superposition states until observed, with uncertainty principles limiting what we can know, with entanglement connecting distant particles instantaneously. But in a universe where macroscopic objects like stars can be perfectly still, quantum mechanics might work differently. Perhaps the uncertainty principle doesn't apply to position in this universe. Objects can have perfectly defined locations, which is why stars can be absolutely motionless. But to balance this, uncertainty in other properties might be increased. Maybe the composition of stars is fundamentally uncertain, constantly fluctuating between different elemental makeups. Or perhaps their internal states exist in permanent superposition, making them quantum objects despite their macroscopic size. The invisible centers that planets orbit might be quantum structures scaled up to astronomical size. In our universe, quantum effects usually average out at large scales, but perhaps the special physics of this cosmos allows quantum phenomena to persist at planetary scales. The invisible centers could be massive quantum superpositions, existing in multiple states simultaneously, only appearing to have gravitational effects when planets observe them through orbital interaction. This leads to an even stranger possibility. Perhaps the planet's orbits around nothing are actually creating the invisible centers through a kind of quantum feedback loop. The act of orbiting might collapse a quantum field into a gravitational well, which sustains the orbit, which maintains the collapse. It would be a self-sustaining system where cause and effect are circularly linked, where planets orbit because they orbit, where the invisible centers exist because planets behave as if they exist. Let's delve deeper into the structure of space itself in this universe. In our cosmos, we think of space as relatively uniform, the same in all directions and locations, at least on large scales. But the space of this imagined universe might be highly structured, with different regions having different properties. There might be crystalline regions where matter can only exist at specific lattice points, explaining why stars are fixed, and fluid regions where orbital motion is possible, where planets exist. The boundaries between these regions would be fascinating places. Perhaps at the interface between crystalline and fluid space, exotic phenomena occur. Matter transforming from mobile to immobile, time flowing at different rates, the laws of physics themselves shifting. These boundaries might be invisible to light but detectable through their effects on matter that crosses them. They might be the walls of cosmic cells, dividing the universe into distinct domains with their own rules and properties. The thermodynamic framework would need to account for a universe where large-scale motion is impossible or highly restricted. In our universe, heat flows from hot to cold, entropy increases, energy spreads out and becomes less useful over time. But if stars can't move and planets orbit nothing, how does heat flow on cosmic scales? How does entropy increase globally rather than just locally? Perhaps heat in this universe flows through dimensions we can't perceive, or through the invisible centers that planets orbit. These centers might be conduits for thermal energy, allowing heat to move between star systems without any visible mechanism. Or perhaps the strange physics that keeps stars still also provides channels for entropy flow, invisible rivers of disorder that prevent any region from becoming too organized or too chaotic. The electromagnetic framework might be radically different as well. In our universe, moving charges create magnetic fields, changing magnetic fields induce electric fields, and these interactions create the electromagnetic waves we see as light. But if stars don't move, and if the charged particles within them are somehow constrained, how does light propagate? Perhaps electromagnetic waves in this universe don't require moving charges to generate them. They might emerge spontaneously from the quantum vacuum, or from the interaction between matter and the strange structure of space itself. This could explain why stars can shine without moving. They might not be generating light through conventional fusion and thermal radiation, but through some exotic interaction with the fabric of space around them. Each star might be a kind of cosmic lighthouse, where the structure of space itself generates light, using the star's mass and composition as a template, but not requiring any motion or conventional energy source. The nuclear framework, the forces that hold atomic nuclei together and govern radioactive decay, might also operate differently. In our universe, nuclear processes are statistical, governed by quantum probabilities. But in a universe with different quantum rules, nuclear processes might be more deterministic or follow different probability distributions. This could affect stellar fusion, making stars burn more steadily or more variably than in our universe, perhaps explaining how they can shine forever without moving or running out of fuel. Let's consider the possibility of what we might call information fields, invisible structures that encode information about how matter and energy should behave in different regions of space. These fields wouldn't carry force or energy in the conventional sense, but would instead carry instructions, rules, algorithms that matter and energy must follow. The invisible centers that planets orbit might be information structures, programs written in the fabric of space that tell planets how to move, even though there's nothing physical to orbit. This information framework might explain the apparent violation of causality in planets orbiting nothing. The information about the orbit, its size, shape, period, could be fundamental, existing independently of any physical cause. Planets wouldn't orbit because gravity pulls them. They would orbit because the information field in that region of space encodes orbital motion. It would be like having the solution to an equation without having the equation itself, the result without the cause. These information fields might be readable by sufficiently advanced technology. Beings in this universe might develop instruments that can detect and decode the information structures underlying reality, reading the cosmic instruction manual directly. They might even learn to rewrite these fields, changing the rules locally, creating regions where different physics applies, perhaps even creating bubbles where stars can move and planets orbit visible masses, recreating something like our universe within their own. The topological framework of space might be far more complex than in our universe. While our space seems to be simply connected on large scales, you can draw any loop and shrink it to a point. The space of this imagined universe might be multiply connected, full of holes and handles and twisted structures. The invisible centers that planets orbit might be topological defects, places where space is knotted or punctured in ways that create gravitational effects without mass. These topological structures might be why stars can't move. They might be pinned to specific topological features like buttons sewn onto fabric. Moving a star would require not just overcoming gravitational inertia, but actually restructuring the topology of space itself, which might be impossible with any finite amount of energy. The stars would be frozen not by force, but by the fundamental structure of the space they inhabit. The framework of time might be the strangest of all. We've already explored how time might flow differently in this universe, but the underlying framework could be even more exotic. Perhaps time isn't a single dimension, but a complex manifold with multiple directions and paths. The invisible centers might be temporal structures, loops or knots in time that create the appearance of spatial orbits. Planets might not be orbiting through space at all, but through time, following closed temporal curves that we perceive as spatial motion. This temporal framework might explain why some things move and others don't. Stars might exist in temporal dead zones where time doesn't flow, making motion impossible. Planets might exist in temporal currents where time flows in circles, creating what appears to be orbital motion. The boundary between these zones might be the invisible centers, not objects in space, but transitions between different temporal regions. As we go deeper into these hidden frameworks, we begin to see that this imagined universe might not be as impossible as it first seemed. It would require different physics, different fundamental structures, different relationships between cause and effect. But it would still be a cosmos governed by rules, even if those rules are utterly foreign to our experience. The frameworks might be hidden, but they would still be there, creating order from what might otherwise be chaos. The search for these hidden frameworks would be the great scientific quest of beings in such a universe. Just as we search for dark matter and dark energy, for quantum gravity and a theory of everything, they would search for the invisible structures that explain their visible reality. They would develop mathematics we can't imagine, instruments that detect properties we don't know exist, theories that would seem like magic or madness to us but would be rigorous science to them. Some scientists in this universe might propose that the hidden frameworks are alive in some sense. Not biological life, but something analogous, structures that process information, respond to changes, perhaps even evolve over cosmic time. The invisible centers might be nodes in a vast cosmic nervous system, the still stars might be memory storage devices, the planets might be sensors or actuators. The entire universe might be a kind of organism, its hidden framework serving as the cosmic equivalent of DNA, metabolism, and consciousness. Others might argue that the frameworks are mathematical rather than physical, that their universe is quite literally made of mathematics, with physical objects being merely the solutions to cosmic equations. The invisible centers would be mathematical singularities, the still stars would be fixed points in cosmic functions, the planets would be periodic solutions to differential equations written in the fabric of reality itself. To understand their universe fully would require not just observing it, but solving it, finding the master equation from which everything else follows. Still others might propose that the hidden frameworks are remnants of a previous universe, or interfaces with other universes, or projections from higher dimensions we can barely conceive. Each theory would make predictions, suggest observations, inspire new technologies to probe deeper into the hidden structures of reality. The science would advance, even if the ultimate truth remained elusive, each generation building on the discoveries of the previous one, slowly assembling a picture of the cosmic architecture that makes their strange universe possible. Now, let us turn our imagination to the most profound question of all. What would it mean to be conscious, to be alive, to be human, or something like human, in a universe where stars never move and planets orbit invisible centers? As you lie there in the comfort of your familiar world, with its reliable sunrise and sunset, its seasons and cycles, its cosmic dance that has shaped every aspect of life as we know it. Try to imagine existence under that still sky, on a world circling nothing, in a cosmos that defies our deepest intuitions about how reality should work. The beings in such a universe, let's call them people, though they might be as different from us as we are from the first bacteria, would have evolved under profoundly different conditions. Their planet, orbiting its invisible center, might glow with its own light rather than basking in the warmth of a star. Their sky would be forever dark except for the distant unmoving stars and, perhaps, the faint luminescence of other planets in their system, each following its own mysterious path around nothing. Their days and nights, if they had them, would come from their planet's rotation alone, not from any sunrise or sunset. From the moment consciousness first flickered into existence on such a world, the questions would be different. Children wouldn't ask why the sun rises and sets. There would be no sun. They might ask instead why their world glows, why the stars never move, why the ground beneath them follows its eternal path through the darkness. The first myths and religions would grapple with different mysteries, not why the sun god drives his chariot across the sky, but why the stars chose their eternal positions, why planets were granted motion while stars were condemned to stillness, what invisible presence anchors their world in its orbit. Picture the first astronomers on such a world, perhaps thousands of years ago in their history, looking up at the unchanging heavens with wonder and confusion. Without the wandering planets that gave our ancestors their first clue that not everything in the heavens was fixed, without the seasonal changes in star positions that revealed Earth's orbit, how would they begin to understand their cosmos? Perhaps they would focus on the only things that do change, the phases of their moons if they have them, the slow drift of neighbouring planets in their separate orbits around other invisible centres, the gradual evolution of their own world. Their mathematics might develop differently, focused more on static relationships than dynamic ones. Where our early mathematics grew from tracking celestial motions and predicting eclipses, theirs might emerge from mapping the eternal positions of stars, finding patterns in their fixed arrangements, discovering the hidden geometries that govern a motionless sky. They might develop a mathematics of stillness, equations that describe permanence rather than change, geometric principles that explain how things can exist without moving. The development of their physics would follow an entirely different path. Without observable stellar motion to inspire theories of gravity and inertia, they might not discover these concepts for millennia. Instead, they might develop theories based on what they can observe: the glow of their world, the invisible force that keeps them in orbit, the mysterious barrier that prevents stars from moving. Their Newton might not discover laws of motion but laws of stillness, principles that explain not why things move but why they don't. Their Einstein might not develop relativity, the relationship between space, time, and motion, but something else entirely, perhaps a theory of absolute position, explaining how objects can have permanent, unchanging locations in space. Their quantum mechanics might focus not on uncertainty and probability, but on the certainty of stellar positions and the mystery of invisible centers. Each breakthrough would reveal new layers of strangeness in their already strange universe. The technology of such a civilization would be shaped by their unique physics. Without stellar motion to use for navigation, they might develop other methods, perhaps detecting the subtle gravitational variations of invisible centers, or reading the quantum signatures of still stars, or navigating by the patterns of their planet's own glow. Their ships, if they built them to explore their world, wouldn't use the stars to find their way but might instead follow the invisible field lines that permeate their reality. Space travel, if they achieved it, would be a different kind of adventure. Without moving stars to provide gravitational slingshots, without stellar wind to catch in solar sails, they would need to develop propulsion methods we haven't imagined. Perhaps they would learn to surf the boundaries between regions of different physics, or tap into the energy of invisible centers, or manipulate the strange forces that keep stars still to achieve motion themselves. Imagine their first attempts to leave their planet, to visit others in their system. They would launch into a dark void, aiming for another glowing world orbiting its own invisible center. The journey would be through true darkness. No sun to light their way, only the distant, unmoving stars and their destination's faint glow growing slowly brighter. Landing on another world, they would find it lit by its own inner light, following its own mysterious orbit, perhaps harbouring its own forms of life that evolved under the same strange sky. The discovery of life on other worlds would raise different questions than it does for us. We wonder if life elsewhere needs water, carbon, and sunlight like Earth life does. They would wonder if life always requires a self-glowing world, if it can only exist on planets that orbit invisible centers, if consciousness somehow depends on the mysterious physics that governs their universe. Finding life on a neighbouring planet wouldn't answer these questions, but deepen them. Is life common in their universe, or did it require an incredibly unlikely combination of circumstances to arise, even on glowing worlds circling nothing? Their search for intelligence elsewhere would take different forms. Without radio waves generated by moving charged particles in stellar atmospheres, the cosmic background might be quieter, making artificial signals easier to detect. But what would those signals say? How would beings communicate across the void when they share no common references, no rising and setting stars, no celestial mechanics that work the same way everywhere? They might develop languages based on the only true universals in their universe, the fixed positions of stars, the properties of invisible centers, the rates at which different types of matter glow. The art and literature of such a civilization would reflect their unique relationship with the cosmos. Their poetry wouldn't speak of sunrise and sunset, of seasonal changes, of stars wheeling overhead. Instead, it might celebrate the eternal light of their world, the mystery of their orbit, the profound stillness of the stars. Their paintings might capture the subtle variations in their planet's glow, the way darkness looks different in different directions, the patterns made by still stars that have watched over every generation exactly the same way. Music might have evolved differently too. Without the rhythms of day and night driven by a sun, without the annual cycles of seasons, their sense of tempo and rhythm might come from other sources: the pulse of their planet's inner light, the period of their orbit around nothing, the quantum vibrations of matter itself. Their instruments might be designed to capture and amplify the silent music of the spheres, the gravitational waves from planets orbiting invisible centers, the electromagnetic whispers of still stars. Their philosophy would grapple with questions we've never had to ask. If the stars have always been still, did the universe have a beginning, or has it always existed in its current state? If planets orbit nothing, what does that mean for cause and effect, for the relationship between existence and purpose? If some things glow and others don't, some things move and others can't, what determines these fundamental categories? Their philosophers might develop schools of thought we can't imagine, perhaps absolutists who believe in the eternal nature of stellar positions, or relativists who argue that stillness and motion are merely different perspectives on the same reality. Religion in such a universe might focus on different aspects of existence. Where many of our religions incorporate solar deities and celestial cycles, theirs might venerate the invisible centers, the unseen anchors that keep their worlds from drifting into the void. They might have creation myths about how the stars were frozen in place, why planets were blessed or cursed with motion, what consciousness brought to a universe of stillness and darkness. Their sacred texts might be star maps, recording not the motion of heavens but their eternal arrangement, finding meaning in patterns that never change. The psychology of beings evolved under a still sky might be profoundly different from ours. Without the natural cycles of day and night, their sleep patterns might be self-generated rather than environmentally triggered. Without seasonal changes, their moods and behaviors might be more stable, or perhaps more dependent on internal cycles we don't experience. The absence of a visible sun might affect their entire emotional landscape. No association of light with warmth and safety, no fear of the dark, since dark is the natural state. No seasonal affective disorders, no circadian rhythms tied to solar cycles. Their medicine would develop in response to different challenges. Without solar radiation, they might not develop skin, cancer, but the constant glow of their planet might cause other problems we can't imagine. Without vitamin D from sunlight, they would need other biochemical pathways for calcium absorption and bone health. Their eyes might be adapted to see in much dimmer light, or perhaps to perceive wavelengths we can't see, detecting the subtle emanations from invisible centers or the quantum glow of still stars. Agriculture, if they developed it, would be based on their planet's own light rather than photosynthesis as we know it. Plants might absorb the planet's glow directly, or tap into the electromagnetic fields generated by their world's passage through space, or feed on the exotic particles emitted by invisible centers. Farmers wouldn't track seasons by the sun's position, but might instead monitor their planet's glow cycles, the intensity of cosmic rays, or other factors we can't imagine. Their cities would be designed differently. Without a sun to provide directional light and shadow, architecture might focus on capturing and channeling their planet's glow. Buildings might be designed as light collectors and distributors, with complex systems of mirrors and lenses to bring the planet's emanation to every corner. Streets might be laid out not in cardinal directions based on solar motion, but in patterns that follow the invisible field lines of their reality. The hidden frameworks we explored earlier. Education would emphasize different knowledge. Children would learn early that their world orbits nothing, that stars never move, that the universe operates on principles that would seem impossible to us. This wouldn't be advanced physics to them, it would be basic reality, as fundamental as learning that the Earth orbits the Sun is for our children. Their textbooks would contain diagrams we would find bizarre. Planets floating in empty space, stars frozen in eternal positions, invisible structures that govern everything but can't be seen. Their relationship with time would be unique. Without celestial clocks, they might develop a more fluid sense of temporality, or perhaps a more rigid one based on atomic clocks and radioactive decay. Historians wouldn't date events by solar years, but by planetary orbits around nothing, or by the slow evolution of their world's glow, or by cycles we can't imagine. The past might feel more present to them with stars that have never moved, or more distant without celestial markers to track its passage. Love and relationships might unfold differently under an eternal sky. Without sunset walks or sunrise proposals, romance would find other expressions. Couples might bond over watching neighbouring planets in their slow orbits, or finding meaning in the patterns of still stars, or sharing the warmth of their world's glow. The metaphors of love would be different, not "you are my sunshine," but perhaps "you are my world's light," or "you orbit the invisible centre of my heart." Death and mortality would be viewed through a different lens. Surrounded by stars that never die, or die so slowly it's imperceptible, death might seem more unnatural, more wrong. Or perhaps the opposite. The permanence of stars might make mortal life seem even more precious, a brief flicker of consciousness in an eternal cosmos. Funeral rites might involve returning the deceased to their planet's glow, or launching them toward invisible centres, or preserving them in hope that the strange physics of their universe might allow resurrection. Their wars, if they had them, would be fought over different resources. Not oil or solar energy, but perhaps access to invisible centres, or regions where their planet's glow is strongest, or materials that interact with the hidden frameworks of reality. Their weapons might exploit the physics of stillness, devices that freeze motion, that sever the connection between planets and their invisible centres, that disrupt the glow of worlds. Peace movements might emphasize the unity implied by their strange cosmos. All planets orbit nothing, all stars are still, all conscious beings share the same mysterious reality. They might develop philosophies of cosmic cooperation based on the idea that in a universe of invisible connections and hidden frameworks, everything affects everything else in ways we can't see. Their environmental movements might focus not on climate change caused by solar variations, but on preserving their planet's glow, maintaining its orbit, protecting the invisible structures that make life possible. As their civilization advanced, they might begin to question whether their universe is the only possible one. Their scientists might theorize about alternate realities where stars move and planets orbit visible masses, where day and night come from something other than planetary rotation, where the cosmos is dynamic rather than static. These theories might seem as strange to them as their reality seems to us, but curious minds would pursue them, building instruments to search for evidence of other universes, other ways for reality to organize itself. Some among them might even detect signals from universes like ours, faint electromagnetic echoes from cosmos where different physics applies. The discovery that motion is possible elsewhere, that stars can wander and planets can orbit suns, would revolutionize their worldview. It would be like us discovering that somewhere the laws of thermodynamics don't apply, that perpetual motion is possible, that cause doesn't always precede effect. The stories they tell their children would be different from ours, not Icarus flying too close to the sun, but perhaps Stellaris trying to move a star and being frozen forever in punishment. Not Prometheus stealing fire from the gods, but Orbitus discovering the secret of the invisible centres and sharing it with mortal kind. Their heroes wouldn't be sun gods and moon goddesses, but the brave explorers who first left their glowing world, the scientists who discovered why stars are still, the philosophers who found meaning in orbiting nothing. And now, as our journey through this impossible cosmos nears its end, as the hours have passed, and perhaps sleep tugs gently at the edges of your consciousness, we begin the slow voyage home, back from a universe where stars stand eternally still and planets orbit invisible centres, back to our familiar cosmos where everything dances in the dark, where motion is as fundamental as existence itself. But we return changed, carrying with us new perspectives on the universe we actually inhabit, new appreciation for the cosmic ballet we take for granted, new wonder at the fact that we exist at all in a cosmos that could have been so utterly different. As you lie there in the darkness, or perhaps dawn is beginning to lighten your window, or afternoon sun slants across your room, depending on where you are on our spinning Earth, feel for a moment the motion we've always known, the Earth rotating beneath you at hundreds of miles per hour, carrying you from night into day and back again. The Earth orbiting our Sun, that faithful star that has warmed our world for billions of years, that drives our weather and seasons, that powers nearly all life through the alchemy of photosynthesis. Our Sun carrying us around the galaxy, a 250 million year journey through spiral arms and stellar neighbourhoods. Our galaxy itself moving through the cosmic web, part of the grand expansion that began with the Big Bang and continues to this moment. All of this motion, all of this cosmic choreography, suddenly seems less inevitable, doesn't it? After imagining a universe where such motion is impossible, where stars are frozen and planets orbit nothing, our moving cosmos seems almost miraculous. The fact that stars can form from collapsing gas clouds, that planets can condense from swirling disks, that gravity can orchestrate such beautiful dances across billions of light years, none of this had to be. The universe could have been still. It could have been empty. It could have been so many things other than what it is. Think about the stars you see at night, or that you know are there even when city lights hide them. Each one is on its own journey through space. Sirius, the brightest star in our night sky, is actually approaching us, growing infinitesimally brighter each year as it draws nearer. In about 60,000 years, it will be at its closest approach, just over 8 light-years away, before beginning to recede again. Betelgeuse, the red giant that marks Orion's shoulder, is moving too, part of the general circulation of stars around our galaxy's centre. Even Polaris, our steadfast North Star, is slowly drifting, and in a few thousand years it will no longer mark true north. This stellar motion, which seemed like a given before our imaginary journey, now seems pregnant with possibility. Every star's movement is a story. Where it came from, where it's going, what encounters it might have along the way. Some stars are racing away from stellar nurseries where they were born, ejected by gravitational interactions with their siblings. Others are falling toward each other, destined to merge in millions of years. Still others are locked in binary dances, spiraling around common centres of mass in partnerships that can last billions of years or end in spectacular supernovae. Our own sun's motion tells the story of our cosmic neighbourhood. We're currently passing through what astronomers call the local interstellar cloud, a region of relatively dense gas about 30 light-years across. In about 20,000 years, we'll emerge from this cloud into a different region of space. Our solar system oscillates up and down through the galactic plane as we orbit, like a horse on a carousel that goes up and down as well as around. These motions affect the cosmic rays that reach Earth, the comets that get disturbed from the Oort cloud, possibly even the climate over very long timescales. But it's not just the grand motions of stars and planets that seem newly precious after our imagined journey. Think about the simple fact that we can have seasons because Earth's axis is tilted as we orbit the Sun, that we can have eclipses because the Moon happens to be just the right size and distance to occasionally cover the Sun perfectly, that we can have meteor showers because Earth passes through the debris trails of comets. All of these phenomena depend on motion, on the cosmic dance that we might have taken for granted before imagining its absence. The development of life itself has been shaped by celestial motion in ways we're only beginning to understand. The tides, driven by the Moon's orbit, may have been crucial for the development of early life, creating tidal pools where chemistry could concentrate and complexify. The day-night cycle has driven the evolution of circadian rhythms in almost all life on Earth. The seasonal cycles have shaped migration patterns, breeding behaviours, hibernation strategies. Even the very long cycles, ice ages driven by variations in Earth's orbit, mass extinctions possibly triggered by our passage through the galaxy's spiral arms, have been crucial chapters in life's story. Our human story too has been written in the language of cosmic motion. Ancient humans navigated by the stars, but only because those stars rose and set, only because their positions changed with the seasons in predictable ways. We developed agriculture by learning to read the celestial calendar, knowing when to plant and when to harvest by the position of the sun and stars. We explored our planet by following the stars across the oceans, using their motion to determine latitude and eventually longitude. Our science has been a dialogue with cosmic motion from the very beginning. The ancient Greeks noticed that planets wandered against the background stars, leading to models of the cosmos that tried to explain this motion. Galileo's observation of Jupiter's moons orbiting the giant planet helped shatter the geocentric worldview. Newton's laws of motion and gravitation were inspired by the Moon's orbit and confirmed by predicting the return of Halley's Comet. Einstein's relativity emerged from thinking about the motion of light and the equivalence of different reference frames. Even our technology depends on cosmic motion in ways we rarely consider. GPS satellites work because we can precisely predict their orbits and account for relativistic effects. Communication satellites stay in geostationary orbits, matching Earth's rotation to hover over the same spot. Weather satellites track storms by observing cloud motion against Earth's rotating surface. Space probes use gravitational slingshots around planets to reach their destinations, turning the solar system's motion into fuel for exploration. But perhaps the most profound gift of our moving universe is the way it connects us to everything else. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were forged in the cores of stars that lived and died before our sun was born. These elements were scattered through space by stellar explosions and stellar winds, mixed in interstellar clouds, incorporated into new stars and planets. We are literally made of stardust, but only because stars move, collide, explode, and scatter their ashes through the cosmos. This cosmic recycling, this gradual enrichment of the universe with heavy elements, wouldn't be possible in a universe of still stars. Each star would burn through its fuel in isolation, unable to share its nucleosynthetic products with future generations. There would be no second-generation stars enriched with metals, no rocky planets formed from the debris of earlier stellar systems, no complex chemistry leading to life. The universe would be a collection of isolated stellar islands, each burning alone in the dark until it exhausted its fuel and died. Our moving universe is also an evolving universe, one with a history and a future. We can look back and see how galaxies formed from tiny density fluctuations in the early universe. We can watch galaxies collide and merge, creating bursts of star formation. We can observe the universe accelerating in its expansion, driven by dark energy. We live in a cosmos with a story, one that began with the Big Bang and will end in ways we're still trying to understand, perhaps a big rip, a big freeze, or something we haven't imagined yet. This cosmic evolution gives meaning to our existence in ways that might not be possible in a static universe. We're not just observers of an eternal, unchanging cosmos. We're participants in an unfolding story. The universe was different before we existed and will be different after we're gone. Our brief moment of consciousness occurs at a particular chapter in cosmic history, when stars still shine and planets still orbit, when galaxies still form, stars and black holes still grow, when the universe is neither too young nor too old for complexity and life to flourish. As we return fully to our moving cosmos, we might also appreciate the mysteries that motion creates. Dark matter reveals itself through the too fast rotation of galaxies and the gravitational lensing of galaxy clusters in motion. Dark energy shows up in the accelerating expansion of the universe. Gravitational waves, those ripples in space-time itself, are created by accelerating masses. Binary black holes spiraling together, neutron stars colliding. Without motion, many of the universe's deepest secrets would remain forever hidden. The search for life elsewhere in our universe is fundamentally a search enabled by motion. We look for exoplanets by watching stars wobble or dim as planets orbit them. We search for biosignatures in the atmospheres of planets as they transit their stars. We listen for radio signals from civilizations that, like us, have learned to harness electromagnetic radiation. We dream of interstellar travel, of riding the cosmic currents to other worlds, of spreading consciousness through a galaxy in motion. Even our questions about the ultimate nature of reality are shaped by living in a moving universe. We wonder about the nature of time because we experience its passage through change and motion. We ponder relativity because motion affects the flow of time and the measurement of space. We explore quantum mechanics partly to understand how particles move and interact. We search for a theory of quantum gravity to reconcile the smooth, continuous motion of general relativity with the discrete, probabilistic jumps of quantum mechanics. But perhaps the most beautiful aspect of returning to our moving sky is the renewed sense of wonder it brings. Every sunrise becomes a miracle, not just light appearing, but our world turning to face our star. Every change of season becomes a cosmic event, our tilted planet leaning toward and away from the sun. Every meteor streak becomes a reminder that we're hurtling through space, occasionally running into the debris of our solar system's formation. Every twinkle of a star becomes evidence of our atmosphere in motion, bending starlight as air of different temperatures mixes above us. The constellations, those patterns that seemed so eternal when we began this journey, now reveal themselves as temporary arrangements. Orion's belt, those 3 stars that have guided humans for millennia, are actually at vastly different distances and moving in different directions. In 100,000 years, Orion will no longer look like a hunter. The Big Dipper is already changing shape as its stars pursue their individual paths through space. The Southern Cross is slowly processing out of southern skies. The patterns we see are snapshots in a cosmic movie that has been playing for billions of years and will continue for billions more. Yet there's something poignant about this. Temporariness, isn't there? The fact that we happen to exist at just the moment when the stars form the patterns we know, when the moon is just the right distance to create perfect solar eclipses, when our sun is in its stable middle age, it makes our moment in cosmic history feel special, precious, irreplaceable. We're not eternal beings in an eternal cosmos, but temporary arrangements of matter that have briefly become conscious in a universe that is itself temporary and changing. This returns us to the deep questions we've been circling throughout our journey. Why does our universe have motion at all? Why do the laws of physics permit and even require change? Could the universe have been otherwise, frozen like the cosmos we imagined, or different in ways we haven't even conceived? These questions don't have answers yet, and perhaps they never will, but the fact that we can ask them, that we can imagine alternatives, that we can appreciate the profound gift of living in a universe where things move and change and evolve, this itself is a kind of answer. Modern cosmology suggests that our universe might be just one of countless others in a vast multiverse, each with its own laws of physics, its own constants of nature, its own possibilities and impossibilities. Somewhere in that multiverse, perhaps there really is a cosmos where stars stand still and planets orbit nothing. Perhaps there are universes even stranger, where time runs backward, where cause and effect are reversed, where consciousness creates reality rather than emerging from it. Our moving universe might be the exception rather than the rule, a rare cosmic jewel where motion and stillness find just the right balance to allow complexity, life, and wonder. As you lie there, perhaps drowsy now after our long journey through impossible spaces, feel once more the motion that surrounds and includes you. Your blood circulating, carrying oxygen to every cell. Your neurons firing, creating the thoughts and dreams that make you who you are. The earth spinning beneath you, carrying you through space at speeds that dwarf any vehicle humans have built. All of this motion, from the quantum to the cosmic scale, working together to create this moment of consciousness, this experience of being. The imagined universe we've explored tonight, with its still stars and planets orbiting nothing, has been a mirror in which to see our own cosmos more clearly. By imagining what isn't, we better appreciate what is. By exploring the impossible, we discover new depths in the possible. By journeying to a universe that never was, we return home to a universe that is stranger, more beautiful, and more precious than we might have realized. Tomorrow, when you wake, or later today, if morning is already approaching where you are, you'll return to the ordinary world of sunrise and sunset, of seasons and years, of a sky that seems stable but is actually in constant, beautiful motion. But perhaps you'll carry with you a little of the wonder we've shared tonight. Perhaps you'll look at the stars, whether visible or hidden by daylight, and marvel that they're all on journeys through space. Perhaps you'll feel the Earth's motion not as something abstract, but as something real and present and miraculous. And perhaps, in quiet moments, you'll remember the universe that never was, where stars are eternal sentinels and planets dance with invisible partners, and feel grateful for the cosmic dance we're all part of. For in the end, that's what we are, temporary patterns in the flowing fabric of space-time, brief arrangements of matter and energy that have somehow become aware of themselves and the cosmos around them. We are the universe's way of knowing itself, of appreciating its own motion, of wondering what else might have been possible. The stars above you, or hidden beyond your ceiling and the bright sky, are not fixed markers but fellow travellers, each on its own journey through the cosmic dark. The planets, including our own Earth, are not wandering aimlessly, but following the beautiful mathematics of gravity and motion, tracing paths that connect us to everything else in the universe. And you, lying there in the darkness or the growing light, are not separate from this cosmic dance, but an integral part of it. Made of star stuff, moved by the same forces that move galaxies, conscious for this brief moment of the grand story in which we all play a part. As our exploration comes to its close, as the imagined universe of still stars and orbiting planets fades back into the realm of thought experiments and possibilities, we're left with a deeper appreciation for the universe we actually inhabit. It didn't have to be this way. The cosmos could have been still, silent, static. Instead, we live in a universe of motion and music, of birth and death and rebirth, of endless creativity and change. We live in a universe where stars wander and planets know their orbits, where galaxies collide and merge, where space itself expands and time flows forward, where consciousness can emerge and contemplate it all. This is the gift of our moving sky, not just that it exists, but that we exist within it, able to perceive and appreciate and wonder at its endless dance. We are not outside observers of cosmic motion, but participants in it, dancers in the cosmic ballet, notes in the universal symphony. Every breath you take is part of this dance. Every heartbeat is a rhythm in the cosmic song. Every thought is a pattern in the flowing fabric of reality itself. So rest now, dear traveller. After our long journey through impossible spaces and back home again, let your consciousness drift towards sleep, or toward waking if morning finds you, carrying with you the wonder of what is and what might have been. The universe continues its dance around you and within you, stars pursuing their ancient paths, planets faithfully circling their suns, galaxies slowly turning in the cosmic dark. And somewhere in all that motion, on a small planet orbiting an ordinary star in an unremarkable galaxy, you exist, a conscious witness to the cosmic dance, a questioner of mysteries, a dreamer of other worlds. The stars that watch over you tonight are not the still sentinels of our imagined universe, but wanderers like yourself, each on its own journey through space and time. The Earth beneath you is not circling an invisible nothing, but faithfully orbiting our sun, that generous star that gives us light and warmth and life itself. And you are not alone in a cosmos of stillness, but part of a vast, moving, evolving universe that somehow, against all odds, has given rise to beings capable of imagining how things might have been different. This is the final gift of our journey, the recognition that our moving universe, with all its complexity and mystery and beauty, is not a prison of deterministic motion, but a dance floor of infinite possibility. Yes, the stars will continue on their paths, and planets will maintain their orbits, and galaxies will wheel through the cosmic dark. But within that grand choreography, there is room for variation, for creativity, for the emergence of new patterns and possibilities. There is room for life, for consciousness, for wonder. There is room for beings like us to look up at the moving sky and ask, what if it were otherwise? And in asking that question, in imagining still stars and planets orbiting nothing, we don't diminish our moving universe but celebrate it. We honour its contingency, its possibility, its profound gift of being rather than not being, of moving rather than standing still, of allowing us to exist and wonder and dream. The universe didn't have to permit consciousness, didn't have to allow life, didn't have to create the conditions for beings who could contemplate their own existence, but it did. And here we are, products of cosmic motion, children of stellar evolution, temporary arrangements of ancient atoms that have briefly awakened to wonder. Sleep now, if sleep is calling you, or wake gently if morning has come, carrying with you the peace of cosmic perspective. The universe that surrounds you is vast and mostly unknown, full of mysteries we've barely begun to explore. But it is also our home, our origin, our destiny. We are not strangers in a strange cosmos, but expressions of the cosmos itself, ways that the universe experiences and knows itself. The motion that seems separate from us is actually our deepest nature. We are motion temporarily organized into form, energy temporarily structured into consciousness, time temporarily aware of itself. And tomorrow, or later today, when you go about your ordinary life in our extraordinary universe, perhaps you'll remember the cosmos that never was, and feel newly grateful for the cosmos that is. Perhaps you'll sense the Earth's motion beneath your feet, feel the sun's warmth with new appreciation, see the stars, visible or invisible beyond the daylight, as the fellow travellers they are. Perhaps you'll carry with you a little of the peace that comes from cosmic perspective, knowing that we're all part of something vastly larger than ourselves, something beautiful and mysterious and always in motion. The dance goes on, with or without our awareness of it. But how much richer life becomes when we recognise ourselves as dancers, when we feel the music of the spheres not as distant harmony, but as the very pulse of our existence. We have imagined tonight a universe of stillness to better appreciate our universe of motion. We have explored the impossible to better understand the actual. We have journeyed to the shores of never was to better see the miracle of what is. And what is this: a universe in motion, stars wandering through space, planets faithfully circling their suns, galaxies slowly turning, space itself expanding, time flowing forward, and in the midst of it all, consciousness awakening to wonder at its own existence. This is the moving sky under which we live, the cosmic dance in which we participate, the grand story of which we are both authors and characters. It is a story without end, a dance without final step, a journey without ultimate destination. And that perhaps is the most beautiful truth of all, that the universe goes on, that motion continues, that the dance never ends, and that we, for this brief precious moment, are part of it all. Good night, or good morning, or good day, wherever and whenever you are. May your dreams be filled with dancing stars and wandering planets, with the music of the spheres and the whisper of cosmic motion. And may you wake refreshed, ready to continue your own journey through our moving, mysterious, magnificent universe. A universe that could have been otherwise, but instead is exactly, miraculously, wonderfully what it is. Our cosmic home, our dancing ground, our moving sky that holds us all in its ancient, eternal, ever-changing embrace.